Imagine standing on the rust-colored surface of Mars, gazing across a landscape that once teemed with water, vast rivers carving through valleys, lakes reflecting a dimmer but familiar sun, and perhaps even the faintest whispers of life. This isn't science fiction. It's a reality buried in the planet's past, waiting to be uncovered. Mars, our enigmatic neighbor, wasn't always the barren desert we see today. Hidden beneath its dusty surface lie the remnants of 37 ancient ecosystems, each a time capsule from a world that could have mirrored Earth in ways we're only beginning to understand. These vanished environments aren't just geological curiosities, they're potential chapters in the story of life itself, stretching far beyond our planet. What if I told you that the clues to extraterrestrial evolution might be locked in these long-lost Martian landscapes? Think about it. Every dried-up riverbed, every mineral deposit, every layered rock formation could hold the answer to one of humanity's most profound questions. Are we truly alone? The search for life beyond Earth isn't just about finding microbes or fossils. It's about piecing together how life might arise, adapt, and even vanish across the cosmos. And Mars, with its eerie parallels to our own world, offers the most tantalizing puzzle of all. This is more than a journey through space, it's a voyage through time. We're about to explore these 37 vanished ecosystems, each one a snapshot of a Mars that could have been. From the towering deltas of Jeziro crater, where NASA Perseverance rover now scours for signs of ancient life, to the mysterious clay-rich plains of Morth valleys, where water once lingered for millennia. These sites are more than just dots on a map. They're windows into a lost world and possibly a blueprint for life elsewhere in the universe. So buckle up. By the end of this exploration, you might never look at the red planet or our place in the cosmos the same way again. Mars today is a frozen desert, a world of dust and rock under a thin, cold sky. But rewind the clock 3 or 4 billion years, and you'd find a planet startlingly similar to early Earth, rivers snaking across its surface, lakes pooling in craters, maybe even an ocean stretching across its northern plains. The evidence is etched into the landscape like ancient handwriting. Take the sprawling network of valleys in the southern highlands, some as deep as the Grand Canyon, carved not by wind but by relentless flows of water. Or the smooth, rounded pebbles discovered by the Curiosity rover, stones shaped by tumbling in a riverbed, just like you'd find on Earth. These aren't just geological oddities, they're snapshots of a Mars that was alive with movement, with cycles of erosion and deposition that mirror our own planet's watery past. What's even more fascinating is how Mars managed to hold onto that water. Unlike Earth, with its strong magnetic field shielding the atmosphere, Mars lost its protective shield early on. Solar winds, those relentless streams of charged particles from the sun, stripped away its air, molecule by molecule, thinning the atmosphere until the planet could no longer trap enough heat to keep water liquid. The lakes dried up, the rivers vanished, the ocean, if it existed, retreated into the soil or froze into the ground. But here's the twist: Mars didn't lose all its water at once. Some lingered underground, seeping out in bursts, carving fresh gullies long after the surface had turned to dust. Some may still be there today, locked in icy layers beneath the soil. This slow, brutal transformation raises a haunting question. If Mars was once so Earth-like, what went wrong? The answer lies in its size. Mars is smaller than Earth, with less gravity to hold onto its atmosphere, and a core that cooled quickly, shutting down the magnetic dynamo that might have shielded it. Without that protection, the planet was vulnerable, its climate unraveling over eons. Yet even in its decline, Mars held onto pockets of habitability, microenvironments where water, warmth, and chemistry could have sustained life. That's why scientists are so obsessed with these lost ecosystems. They're not just studying a dead world, they're piecing together the story of how a planet's fate can change and what that means for life's chances across the cosmos. Think about the implications. If Mars could go from lush to lifeless, what does that say about other Earth-like worlds? Could the same forces, lost atmospheres, dying magnetic fields, silence potential biospheres elsewhere? Or could life, once sparked, cling on in hidden refuges waiting to be found? Every dry riverbed, every mineral stain left by vanished water is a clue. And with rovers like Perseverance drilling into ancient lakebeds and orbiters mapping underground ice, we're closer than ever to reading that story. The Martian Paradox isn't just about a world that died. It's about understanding how worlds live, change, and maybe, just maybe, leave traces of life behind. Picture a vast, shimmering ocean stretching across Mars' northern hemisphere, a body of water so immense it could have rivaled Earth's Arctic Sea. This isn't just speculation. The clues are written into the planet's very terrain. Satellite images reveal sprawling, flat plains in the north, their surfaces unnaturally smooth compared to the rugged southern highlands. These plains bear the hallmarks of an ancient seabed, shaped by sediments settling over millennia. But the real smoking gun, the minerals, hematite, a rust-like compound that forms in water, dots the region like breadcrumbs left behind by a vanished tide. Then there are the clays, layered, delicate minerals that only develop where water lingers for long periods. Together, they paint a portrait of a Mars that was once profoundly wet, a world where waves might have lapped against rocky shores under a pink-tinged sky. But here's where it gets even more intriguing. Water isn't just a geological curiosity, it's the universal solvent for life as we know it. If Mars had a northern ocean, even for a fleeting cosmic moment, it could have been a cradle for microbial life. Think of Earth's earliest organisms thriving in the deep sea around hydrothermal vents. Mars' ocean might have offered similar niches, warm, mineral-rich waters where simple life could have gained a foothold. The challenge: Mars' climate collapsed. As the atmosphere thinned and temperatures plummeted, this ocean would have shrunk, retreated, and eventually frozen over, leaving behind only whispers of its existence. That's why scientists are so fixated on this region. If life did emerge there, its remnants, or even its last survivors, might still be hiding in the sediments, waiting to tell their story. The Northern Ocean hypothesis isn't just about solving a Martian mystery. It's a test case for how life might respond to planetary catastrophe. Imagine a scenario where a habitable world begins to die. Does life cling on in shrinking refuges, adapting to harsher conditions, or does it vanish entirely, leaving only chemical traces behind? Mars' northern plains could hold the answers. NASA Perseverance rover, though exploring Jeziro crater farther south, is laying the groundwork for future missions that might one day drill into these ancient seabeds. Every layer of sediment analyzed, every mineral mapped, brings us closer to understanding whether life ever stirred in those waters, and what its fate might mean for other ocean worlds, from Europa's icy depths to the distant exoplanets orbiting alien suns. What's haunting is the timescale. Mars' ocean, if it existed, likely persisted for hundreds of millions of years, more than enough time for life to emerge. But unlike Earth, where plate tectonics continually recycle the crust, Mars' surface is frozen in time. Its seabeds weren't swallowed and remelted. They were preserved like pages in a cosmic history book. That means the evidence, however faint, might still be readable. the real challenge, distinguishing between the signatures of sterile water and water that once teemed with life. It's a needle in a haystack problem, but one with staggering implications. If we can prove life arose independently on two worlds in our own solar system, the universe suddenly becomes far more hospitable, far more alive in ways we've only begun to imagine. So as we stare at those smooth northern plains from orbit, we're not just looking at a geological oddity. We're gazing at what might have been a second Genesis, a parallel experiment in how life begins and how it ends. The story of Mars' northern ocean isn't just about water lost to time. It's about the resilience or fragility of life itself when faced with a universe that giveth and just as easily taketh away. Now let's journey to Arabia Terra, a sprawling highland region on Mars etched with intricate networks of ancient river valleys, some stretching longer than the Mississippi. These aren't just faint scratches on the surface, they're deep, branching channels that tell the story of a time when rain fell steadily and rivers carved their paths across the Martian landscape. Unlike the sudden floods that created other valleys on Mars, these waterways suggest something far more Earth-like, persistent, seasonal flows that could have lasted for millions of years. Picture a landscape where water didn't just appear in catastrophic bursts but lingered, shaping the land gradually, a place where life, if it existed, might have had the stability to take root. What's striking about Arabia Terra's river networks is their resemblance to systems on Earth. Some valleys fork and weave like tributaries in the Amazon basin, while others fan out into deltas where water once met standing lakes or seas. These patterns hint at a hydrological cycle far more complex than we once imagined for Mars, one with rainfall, evaporation, and even groundwater recharge. And where there's long-term water, there's potential for life. On Earth, river systems teem with microbes even in harsh environments, from the acidic Rio Tinto in Spain to the frozen streams of Antarctica. If Mars had similar rivers, could their muddy banks or mineral-rich sediments have harbored tiny organisms? The clues might lie in the chemistry. Arabia Terra's rocks are rich in clays and sulfates, minerals that form in the presence of water and often trap organic material. On Earth, these same minerals preserve fossilized microbes for billions of years. That's why scientists are so keen to explore this region. If life ever existed here, its molecular fingerprints could still be locked in those rusty layers. But there's a catch. Arabia Terra is also one of the oldest surfaces on Mars, battered by radiation and dust storms for eons. Any evidence would be incredibly fragile, like a message written in sand and left to weather the ages. Yet even the absence of life here would be revealing. If these rivers flowed for so long without fostering biology, it could mean life demands more than just water and minerals, perhaps a specific cocktail of elements, or a stability Mars couldn't sustain. Or maybe life did arise only to be snuffed out as the planet dried. Every twist in these ancient valleys is a question waiting to be answered. Future missions might drill into these river sediments, searching for the faintest traces of carbon or cellular structures. Until then, Arabia Terra stands as a monument to Mars' lost potential, a world that once mirrored Earth's rhythms, only to fall silent under a fading sun. What's haunting is the scale of time involved. These rivers didn't vanish overnight. They shrank, shifted, and faded over millennia, their waters retreating as Mars' climate unraveled. The last drops might have seeped into the ground, leaving behind only dry riverbeds and the echoes of a planet that could have been. But in their stillness, they hold a lesson: habitability isn't permanent. A world can be lush and alive only to become a desert, and that's a truth that reaches far beyond Mars, reminding us that even Earth's vibrant biosphere is a fleeting moment in cosmic time. Deep within Gale crater, a sprawling basin near Mars' equator, lies one of the most compelling chapters in the planet's watery past. NASA's Curiosity rover has spent years crawling across this ancient lakebed, uncovering layer upon layer of sedimentary rock, each one a page in a geological diary stretching back billions of years. These aren't just ordinary rocks, they're snapshots of a time when this crater held a lake so persistent, it could have rivaled Earth's Great Lakes in both size and longevity. Picture a body of water so stable, it existed for millions of years, its shores shifting subtly under a pale pink sky. But what makes Gale crater truly extraordinary isn't just the water it once held, it's what that water left behind. Curiosity's drill has revealed something astonishing buried in those layers: organic molecules, not proof of life itself, but the carbon-rich building blocks that make life possible. Think of them as cosmic Lego pieces scattered through the sediment. On Earth, these same molecules are the foundation for everything from bacteria to blue whales. Finding them on Mars raises an electrifying question. If the ingredients were present, along with liquid water and energy from the sun, could life have assembled itself here too? The lakebed's chemistry adds fuel to the fire. Minerals like hematite and clay suggest not just water, but water with the right pH and salinity to be hospitable. It's as if Mars set the table for life, but we're still searching for the guest list. Yet Gale crater's story doesn't end with its lake. The layers tell a tale of dramatic change. As Curiosity climbed the slopes of Mount Sharp, the crater's central peak, it found younger rocks bearing fewer signs of water, a chronicle of Mars' slow drying. The lake shrank, became intermittent, and finally vanished, leaving behind only mud cracks and mineral veins. But here's the twist. Even as the surface water disappeared, groundwater might have persisted. Curiosity detected liquid brine salty water seeping through cracks long after the lake was gone. That means life, if it ever existed here, could have retreated underground, clinging to dwindling oases in the rock. The real mystery isn't just whether life emerged in Gale crater, but what silenced it. Was it the loss of the atmosphere, the freezing temperatures, or something more subtle? The crater's layers hold clues. Sulfur-rich minerals suggest volcanic activity, while shifts in sediment types hint at climate swings. It's a puzzle with implications far beyond Mars. If life flourished here and then died out, it's a cautionary tale for habitability elsewhere in the universe. But if it found a way to survive underground, even for a time, it rewrites our understanding of how tenacious life can be. Gale crater is more than a fossilized lake. It's a laboratory for cosmic what-ifs. Every scoop of dirt analyzed by Curiosity brings us closer to answering whether life is a cosmic fluke or a universal inevitability. And as the rover continues its climb, one thing becomes clear: Mars wasn't just wet, it was patient, preserving its secrets in stone, waiting for a tireless machine from Earth to come read them. Beneath the cracked and cratered surface of Mars' Arcadia Basin lies a haunting possibility, a network of hydrothermal vents that once churned with scalding, mineral-rich water. This isn't just another dry lakebed or forgotten river valley. These vents, if they existed, would have been something far more extraordinary. Underground oases, powered not by sunlight but by the planet's own heat, creating pockets of warmth in an increasingly cold world. On Earth, hydrothermal vents are teeming with life crabs, tube worms, and microbes thriving in total darkness, fueled by chemicals bubbling up from the planet's depths. If Mars had its own versions, they could have been the last refuge for life as the surface dried up and the atmosphere vanished. The Arcadia Basin is a ghost of this potential. Orbital scans reveal towering deposits of minerals like silica, and sulfates telltale signs of hydrothermal activity. These aren't just random stains, they're the residue of water heated by magma gushing through cracks in the crust. Picture a Martian vent, a fissure spewing steaming water into a submerged cavern, its walls crusted with crystals, its currents swirling with dissolved metals. Unlike surface lakes, which depended on a stable climate, these vents could have remained active long after Mars turned to ice. They'd have been shielded from radiation, buffered against temperature swings, a sanctuary where life, if it ever existed, might have clung on for millions of years. But here's the catch: hydrothermal vents don't last forever. As Mars' interior cooled, the heat source fueling these systems would have dwindled. The vents would slow, then stop, their life-giving chemistry grinding to a halt. For any organisms relying on them, it would be like a city losing its power grid one by one, the lights going out. This raises a chilling question: how does life respond when its energy source vanishes? On Earth, vent ecosystems are resilient but localized. If their vents go cold, the organisms die. But what if Martian life had more time to adapt? Could it have found a way to hibernate or migrate to deeper, warmer cracks in the planet's crust? The search for answers lies in Eridania's rocks. Future missions could drill into those mineral deposits, hunting for fossilized microbial mats or chemical signatures of ancient metabolisms. Even more tantalizing, some scientists speculate that residual heat might still linger in Mars' depths, meaning dormant vents could, theoretically, reactivate. It's a long shot, but if true, it would rewrite our understanding of where life could survive in the cosmos. After all, if a planet as hostile as modern Mars still hides whispers of warmth underground, what does that mean for icy moons like Europa or Enceladus, where oceans slosh beneath miles of ice? Eridania's vents are more than a geological curiosity. They're a test case for life's tenacity in the universe. Their story doesn't just ask whether life existed on Mars, it asks how long life can endure when a planet's heart grows cold. And in their silence, they offer a humbling lesson. Even the hardiest ecosystems are at the mercy of the energy that sustains them. As we peer into the basin's depths, we're not just studying Mars. We're probing the limits of life itself. Hidden beneath the swirling ice caps of Mars' South Pole lies one of the most enigmatic possibilities in our search for extraterrestrial life: ancient subglacial lakes frozen in time. Unlike the dried-up riverbeds and empty lake basins we've explored so far, these potential reservoirs may still exist today, locked under miles of ice and dust. Picture a dark, frigid world where liquid water persists not because of a friendly climate, but thanks to the insulating power of ice above and geothermal heat from below. On Earth, places like Antarctica's Lake Vostok have shown us that life can thrive in such extreme isolation, cut off from sunlight and the surface for millions of years. Could Mars' polar ice hold similar secrets? The evidence is tantalizing. Orbital radar scans have detected bright reflections beneath the South Polar ice signatures that strongly resemble those of liquid water layers here on Earth. These potential lakes aren't just shallow puddles. Some may span tens of kilometers, kept from freezing by the immense pressure of overlying ice and dissolved salts acting like antifreeze. It's a delicate balance, one that hints at an underground plumbing system far more complex than we ever imagined for Mars. And where there's persistent liquid water, especially in stable environments shielded from radiation, the odds of finding preserved organic material or even dormant life rise dramatically. What makes these subglacial lakes so fascinating isn't just their potential to harbor life, but their incredible preservation power. Ice acts as a time capsule. On Earth, scientists have revived microbes trapped in glacial ice for hundreds of thousands of years. On Mars, where geological activity has been minimal for eons, any organisms entombed in polar ice could be preserved in near-perfect condition, their cellular structures intact. The challenge reaching them, drilling through Mars' polar ice, would require technology far beyond our current rovers. Think heated probes capable of melting through kilometers of ice while avoiding contamination. Yet the payoff could rewrite biology textbooks. The implications stretch beyond Mars. If life existed in these icy refuges, it would prove that biology can adapt to environments we once considered utterly inhospitable. That knowledge would revolutionize our search for life on icy moons like Europa and Enceladus, where global oceans slosh beneath frozen shells. But even if Mars' subglacial lakes prove sterile, their very existence tells a profound story about planetary resilience, how water, the universal solvent of life, can outlast even a world's climatic death throes. Future missions are already eyeing the South Pole. Advanced radar instruments could map these hidden reservoirs in greater detail, while robotic drills might one day penetrate the ice, seeking the dark, quiet waters below. What they find or don't find will answer one of astrobiology's biggest questions. Is life a cosmic imperative or an earthly fluke? The ice-covered lakes of Mars' South Pole aren't just geological oddities. They're frozen testaments to life's potential, waiting for us to listen. Jeziro crater isn't just another dry basin on Mars, it's a time machine. Imagine standing on the edge of this ancient lakebed, where 3.5 billion years ago, a river cascaded over the crater's rim, carrying sediments that settled into a sprawling delta. This isn't just geological poetry. That delta, now frozen in time, is one of the most promising places we've ever found to hunt for signs of extinct Martian life. Why? Because deltas are nature's archivists. On Earth, river deltas like the Mississippi or the Nile bury and preserve organic material with incredible efficiency. Leaves, microbes, even dinosaur bones get trapped in their layers, sealed away for millennia. Jeziro's delta, now a fossilized fan of rock, could hold the same treasures, except these might belong to organisms we've never seen, from a world we're only beginning to understand. Perseverance didn't land in Jeziro by accident. Scientists chose this spot because the crater's history reads like a recipe for life. First, water, and not just a fleeting puddle. The lake here was deep and long-lived, possibly spanning millions of years. Second, energy. The rivers feeding it would have carried minerals and nutrients, creating a chemical playground for potential microbes. And finally, preservation. That delta's layers are like pages in a book, each one capturing a moment in time when organic molecules, or even cellular structures, could have been entombed in mud and turned to stone. The rover's mission isn't just to scratch the surface, it's to drill into these layers, collect samples, and ultimately send them back to Earth for analysis. What makes Jeziro so special is its clarity. Unlike other Martian sites where water came and went in chaotic floods, this crater's delta formed gradually, its sediments settling in predictable patterns. That means scientists can read its history like a timeline. The deeper Perseverance drills, the further back in time it travels. Already, the rover has found carbonates and clays minerals that on Earth are notorious for trapping and preserving biosignatures. But the real jackpot would be stromatolites, layered structures formed by microbial colonies. On our planet, stromatolites are some of the oldest fossils we have, dating back 3.5 billion years. If Jeziro holds something similar, it would suggest life on Mars arose in nearly the same way and at the same time as it did here. Yet even if Perseverance finds nothing, the silence would speak volumes. A sterile Jeziro would force us to ask why Mars, despite all its Earth-like ingredients, might have missed the spark. Was the water too acidic? Did the planet's magnetic field collapse too soon? Or is life rarer in the universe than we hoped? Every sample the rover caches is a potential answer, a clue to whether we're alone or part of something vast and interconnected. Jeziro's delta isn't just a scientific target, it's a mirror reflecting our deepest questions about life's cosmic odds. As Perseverance rolls across this ancient lakebed, its wheels are tracing the shoreline of a vanished world. The rocks it drills might hold echoes of organisms that thrived under a younger sun, in waters that once shimmered under Martian skies, or they might whisper a different truth, that habitable doesn't always mean inhabited. Either way, Jeziro's story isn't just about Mars. It's about the fragility of life's foothold in the universe and whether planets like ours are the rule or the rarest of exceptions. Sertis Major isn't just another dark smudge on Mars' surface. It's a sprawling volcanic plateau where fire and water may have once mingled in ways that could have rewritten the story of life itself. Picture this: vast networks of hot springs bubbling up through cracks in the planet's crust, their steam curling into a thin, rusty sky. These wouldn't have been ordinary pools. Like Yellowstone's otherworldly geothermal features, they'd have been rich with minerals, their waters heated not by the sun but by the restless magma beneath. On Earth, such places are teeming with extremophiles microbes that thrive in scalding, acidic, or chemically hostile conditions. If Mars had its own version of these geothermal oases, they could have been perfect incubators for life, offering warmth, energy, and protection from a dying planet's harsh surface. The evidence lies in Sertis Major's geology. Orbital scans reveal patches of silica and sulfate deposits, minerals often left behind when hot water interacts with rock. Some formations even resemble the terraced steps of earthly hot springs, where mineral-rich waters evaporate and leave behind cascading layers of stone. But what's really tantalizing is the timing. Sertis Major's volcanic activity overlapped with the period when Mars was losing its surface water. While rivers dried up and lakes froze over, these underground heat sources could have kept pockets of water liquid far longer, creating refuges where life might have clung on. Imagine a Martian microbe, not unlike those in Yellowstone's hot springs, metabolizing sulfur or iron instead of oxygen, thriving in a crack in the rock while the world above turned to dust. Yet these springs wouldn't have lasted forever. As Mars' interior cooled, the volcanic fires feeding them would have dimmed, the waters would have drained or frozen, and any life dependent on them would have faced a slow extinction unless it found a way to adapt. This raises a haunting parallel to Earth's own history. Some scientists believe our planet's earliest life might have emerged in similar hydrothermal environments, then migrated to milder habitats as conditions changed. Could Martian life have attempted the same leap, or did it perish with its geothermal lifelines? The answer might lie in the chemical fingerprints left behind. If future missions could drill into Sertis Major's mineral deposits, they might find fossilized microbial mats or isotopic ratios that hint at ancient metabolic processes. What makes Sertis Major so compelling isn't just the possibility of past life. It's the lesson it offers about habitability limits. Volcanic hot springs represent a planet's last stand against the cold, a final burst of warmth before the silence sets in. Their demise on Mars would mark the point where geological activity could no longer sustain even the hardiest ecosystems, and that's a boundary we don't yet understand. How long can a planet's inner fires support life after its surface becomes uninhabitable? Could there still be traces of heat deep beneath Sertis Major, enough to keep a trickle of water liquid? The questions don't just apply to Mars. They echo across the cosmos, from the icy moons of Jupiter to the exoplanets orbiting distant stars. Exploring Sertis Major isn't just about uncovering Mars' past. It's about testing the universal rules of survival. If life could endure here in the fleeting warmth of volcanic springs, it might persist in places we've never thought to look. And if it couldn't, well, that too would tell us something profound about the fragility of living worlds. Every mineral stain, every cracked terrace in this ancient volcanic field is a clue, waiting to reveal whether life is a fleeting spark or a force that can outlast even a planet's dying breath. Valles Marineris isn't just a scar on Mars' surface, it's a colossal labyrinth of canyons so vast it would stretch from New York to Los Angeles if placed on Earth. But beneath its towering cliffs and sun-baked plateaus, there's growing evidence of a hidden world, a network of underground aquifers that may have once served as the planet's last reservoirs of liquid water. Imagine water seeping through porous rock, pooling in dark chambers shielded from the harsh surface conditions, a subterranean refuge where life, if it ever existed, could have outlasted Mars' drying climate. On Earth, aquifers are lifelines. In places like the Sahara or the Australian outback, these hidden water tables sustain entire ecosystems, from microscopic organisms to plants with roots that tap into the damp depths. Mars' aquifers, if they functioned similarly, could have offered stability long after the planet's rivers evaporated and its lakes turned to dust. The clues lie in the canyon's geology. Orbital radar has detected signs of water bearing minerals deep beneath Valles Marineris, while certain landforms like collapsed pits and layered deposits hint at ancient groundwater movement. These aren't just dry cracks in the ground, they're fingerprints of a once active plumbing system where water may have circulated for millennia. What's fascinating is how these aquifers might have worked. Unlike surface water, which would have frozen or evaporated as Mars' atmosphere thinned, groundwater could have remained liquid at depth, insulated by overlying rock and warmed by geothermal heat. Some models suggest these reservoirs might have even erupted occasionally, bursting to the surface in short-lived springs before retreating again. That means life, if present, wouldn't have needed sunlight, just chemistry and a steady trickle of water. On Earth, we've found microbes thriving in similar conditions, from the flooded caves of Mexico to South Africa's gold mines, where they live off dissolved minerals and rock-derived energy. Could Martian organisms have done the same? Yet the story of these aquifers isn't just about persistence, it's about escape routes. As Mars' surface grew inhospitable, any surviving life might have faced a stark choice: adapt or perish. Underground water networks could have provided a pathway, a way to migrate deeper as conditions worsened. But here's the haunting part: even aquifers have limits. Over time, Mars' cooling interior would have starved them of heat, and the water would have either frozen or drained away. The final refuge would have vanished, leaving behind only dry fractures and empty chambers. The search for answers isn't just academic. If life did retreat into these hidden pockets, its traces might still be there, preserved in the minerals that once lined the aquifer walls. Future missions could target these depths, drilling or using penetrators to sample the subsurface. What they find or don't find would reveal whether life can exploit even the most fleeting sanctuaries. Valles Marineris aquifers are more than geological relics. They're a test of life's ingenuity in the face of a dying world. And as we peer into those shadowed depths, we're not just studying Mars. We're asking whether life, once sparked, can ever truly be extinguished, or if it simply finds the cracks and waits. Meridiani Planum isn't just another dusty plain on Mars. It's a sprawling graveyard of vanished water, where the ghosts of ancient lakes and seas linger in the form of glittering sulfate salts. Walk across this region today, and your boots would crunch over crystals that formed billions of years ago, as briny water evaporated under a thinning atmosphere. These aren't just pretty minerals, they're chemical time capsules. On Earth, places like Chile's Atacama Desert or Death Valley's Badwater Basin teach us that salt flats are far from lifeless. They're oases for extremophiles microbes that thrive in the harshest conditions, turning salt and sunlight into survival. If Mars ever hosted life, these salts might be its last hiding place. What makes Meridiani Planum so special is its sheer abundance of sulfates. The Opportunity rover, which spent years exploring this region, found veins of gypsum and layers of salt stretching as far as its cameras could see. These deposits tell a story of water that wasn't just fleeting, but cyclical, evaporating, refilling, and evaporating again, like a bathtub draining and filling with each Martian season. Every cycle would have concentrated nutrients and organic material, just as Earth's salt flats do. In places like the Atacama, that very process creates microhabitats where microbes cluster in tiny brine droplets, shielded from the desert's killing dryness. If Mars had similar organisms, their molecular echoes could still be trapped in those crystalline lattices, preserved like insects in amber. Yet the challenge is monumental. Salt preserves, but it also disguises. Detecting fossilized microbes in these minerals would be like finding a needle in a stack of glittering needles. On Earth, we've learned that life in salt flats often leaves behind subtle calling cards, lipid residues, isotopic imbalances, or even DNA fragments. But Mars' salts have been bombarded by radiation for eons, which could scramble or erase those delicate signals. That's why scientists are so fixated on Meridiani's deeper layers. If any biosignatures survived, they'd likely be buried beneath the surface, shielded from the worst of the cosmic rays. The irony is poetic. These salts, born from the death of Martian water, could now be the very thing keeping evidence of life intact. It's a paradox we've seen before. In Earth's harshest deserts, life doesn't just endure. It adapts, exploiting every crack and crevice. If Mars followed the same playbook, Meridiani's salts might hold the ultimate surprise, proof that life, once sparked, can cling on in even the most unforgiving places. Future missions could drill into these deposits, hunting for the faintest chemical whispers of what might have been. Until then, the salt flats stand silent, their crystals glinting with unanswered questions. Hella's Basin isn't just another crater on Mars. It's a colossal depression so vast it could swallow the Grand Canyon whole. But look closer, and you'll find ghostly traces of a world that once shivered under glaciers, their icy fingers carving valleys into the basin's rugged floor. These aren't just frozen relics, they're clues to a time when Hellas was a land of ephemeral lakes and rushing meltwater, a place where life, if it existed, might have clung to the edges of retreating ice. Picture a Martian version of Earth's high Arctic, a landscape where glaciers advanced and retreated with the seasons, leaving behind pockets of liquid water in their wake. For microbes adapted to the cold, these icy oases could have been a last sanctuary as Mars grew colder and drier. The evidence lies in Hella's peculiar landforms. Orbital images reveal sinuous ridges that look like ancient riverbeds, winding their way across the basin's floor. Some scientists believe these were carved not by steady rivers, but by torrents of meltwater bursting from beneath glaciers, a phenomenon we see on Earth when warming temperatures cause ice dams to fail. Elsewhere, there are smooth, flat patches that resemble the beds of long-vanished lakes, their shores etched by the slow grind of ice. These features suggest a dynamic environment, one where water came and went in fleeting bursts, creating temporary habitats that flickered in and out of existence. What's fascinating is how resilient glacial ecosystems can be. On Earth, places like Antarctica's dry valleys or Greenland's ice sheets host microbes that thrive in sub-zero temperatures, surviving in thin layers of liquid water between ice crystals. These organisms don't need sunlight or warm temperatures, just a trickle of meltwater and a source of chemical energy. If Mars had similar life, Hela's glaciers could have offered the perfect refuge, especially as the planet's surface grew hostile. The ice would have shielded organisms from radiation, while meltwater provided a lifeline. But here's the catch: glacial habitats are fragile. A slight shift in temperature or snowfall can erase them entirely. On Mars, where the climate was collapsing, these icy sanctuaries would have been the first to vanish. The real mystery isn't just whether life existed here, it's how long it could have endured. Hela's glaciers might have persisted longer than most surface water, thanks to the basin's depth. As Mars' atmosphere thinned, Hela's, with its lower elevation, could have retained slightly higher air pressure, allowing ice to melt at its edges even as the rest of the planet froze. That means life here might have had extra time, a few precious millions of years to adapt or retreat underground. But did it? The answer could lie in the basin's sediments. Future missions might drill into these ancient lakebeds, searching for the chemical fingerprints of organisms that once danced on the razor's edge between survival and extinction. Hela's glacial valleys are more than a geological curiosity. They're a testament to life's tenacity and its limits. If microbes did flourish here, only to be snuffed out as the ice retreated, it would remind us how narrow the window of habitability can be. But if they found a way to persist, even for a time, it would suggest life can exploit even the most transient opportunities. As we study these frozen landscapes, we're not just unraveling Mars' past. We're learning how life, against all odds, might find a way, or meet its end, on worlds far beyond our own. A Cydalia Planitia's cracked, uneven surface hides one of Mars' most peculiar geological features: fields of ancient mud volcanoes frozen in time. These aren't your typical lava-spewing mountains. Imagine instead a landscape dotted with low, dome-like mounds, their slopes streaked with dried sediment that once oozed from deep below. On Earth, places like Azerbaijan's Gobestan or the Caribbean's Trinidad show us how mud volcanoes behave. They're nature's pressure valves, releasing slurries of water, gas, and minerals as subterranean forces push them upward. But on Mars, these formations aren't just geological oddities, they're potential time capsules, holding secrets about the planet's wetter, more dynamic past. What makes these mud volcanoes so intriguing is what they might have carried to the surface. On Earth, similar structures often belch methane, a gas that, in certain contexts, can be a telltale sign of microbial activity. Deep underground, where sunlight and oxygen are absent, some microbes produce methane as a byproduct of their metabolism. If Martian mud volcanoes once released plumes of methane, could that gas have been a whisper of subsurface life? The possibility isn't far-fetched. Mars' thin atmosphere contains traces of methane even today, though its origin remains hotly debated. Some scientists argue it could be geological, produced by reactions between water and rock. Others wonder if ancient microbes, if they ever existed, might have left behind reservoirs of the gas that occasionally seep out. Either way, Cydalia's mud volcanoes could have been conduits, ferrying clues from the depths to the surface where we might one day find them. Yet the mystery deepens when you consider why these volcanoes fell silent. Unlike Earth's active mud vents, which continue to gurgle and shift, Cydalia's are eerily still. Did Mars' subsurface water dry up, starving the system of its lubricating fluid? Or did the planet's cooling interior cut off the heat that once kept the mud flowing? The answer might lie in the minerals these volcanoes left behind. On Earth, dried mud volcanoes leave behind telltale layers of clay and salts materials that can trap and preserve organic molecules. If Martian microbes ever thrived underground, their remains could be entombed in these very sediments, waiting for a rover's drill to uncover them. The implications stretch beyond a Cydalia. If mud volcanoes were once common on Mars, they could have created a hidden network of refuges, linking subsurface habitats across vast distances. Picture a microbe living in a deep aquifer, swept upward by a mud eruption, then deposited on the surface to be fossilized. It's a long shot, but not impossible. And that's what makes these unassuming mounds so compelling. They're not just relics of water, but potential highways between Mars' buried past and our search for answers. Future missions could target a Cydalia's mud volcanoes, sampling their layers for organic material or isotopic signatures that hint at ancient gas emissions. Until then, these quiet domes stand as silent sentinels, guarding secrets about what might have stirred beneath Mars' surface, and whether, for a fleeting moment, the universe breathed life into the mud. Utopia Planitia stretches across Mars' northern hemisphere like a vast, silent desert, but beneath its windswept surface lies evidence of something extraordinary. Orbital images reveal faint, wavy ridges that curve across the plain like bathtub rings, tracing what many scientists believe are the shorelines of an ancient sea. Not a fleeting lake or temporary flood, but a body of water so expansive it could have rivaled Earth's Caspian Sea in size. Picture this, a shallow Martian ocean, its surface rippling under a pinkish sky, its waters tinted rusty red by dissolved iron. Unlike the planet's more turbulent river systems, this sea would have been stable, enduring for millions of years, long enough, perhaps, to foster its own unique ecosystem. What makes Utopia's potential sea so compelling is its resemblance to vanished bodies of water on Earth. Think of the Paratethys Sea, a Eurasian mega-lake that dried up just a few million years ago, leaving behind the Black and Caspian Seas as remnants. Like Utopia, Paratethys was shallow, its waters rich in salts and minerals, conditions that allowed specialized microbes and even simple multicellular life to thrive along its shores. If Mars' northern sea followed a similar blueprint, its sediments might hold fossilized evidence of organisms adapted to brackish waters or tidal pools. Parallels don't stop there. Both seas vanished due to climate shifts, Earth's due to tectonic movements altering waterways, Mars from atmospheric loss. The difference: on Earth, life had time to migrate or adapt. On Mars, the drying may have been a death sentence. The proof lies in Utopia's chemistry. China's Zhurong rover, which explored part of the plain, detected hydrated minerals like sulfates and clays, compounds that typically form in standing water. Even more telling are the polygonal cracks patterning the ground, identical to the mud cracks found in dried lakebeds on Earth. These features suggest Utopia's sea didn't vanish overnight. It likely shrank gradually, its waters evaporating and leaving behind concentrated brines where hardy microbes might have clung to existence. On Earth, places like Utah's Great Salt Lake show how extreme such environments can become, yet life persists, with salt-loving halobacteria turning the water pink. If Martian organisms existed, could they have endured in Utopia's shrinking pools, evolving to survive ever higher salinity until the last drop was gone? The haunting question isn't just whether life existed here, it's what its extinction might reveal. Earth's fossil record shows mass extinctions where marine ecosystems collapsed due to acidification or oxygen loss. Utopia's sea, if it hosted life, could represent a cosmic case study in how biospheres respond when their lifeblood, water, disappears. Future missions might drill into these dried seabeds, searching for layered microbial mats or chemical imbalances that hint at past biology. Until then, Utopia Planitia stands as a monument to impermanence, its cracked surface whispering of a time when Mars, like Earth, was a world where seas could rise, fall, and vanish, taking their secrets with them. Stretching across Mars' mid-latitudes, Arcadia Planitia's frozen plains hide a secret beneath their dusty surface, a layer of permafrost, ground frozen so solid it's endured for billions of years. Unlike the planet's polar ice caps, this permafrost isn't a glittering sheet of white. It's a silent, buried reservoir, a mix of soil and water ice locked in a deep freeze. But here's what makes it extraordinary. On Earth, permafrost is a time capsule. In Siberia and Alaska, scientists have revived microbes frozen for millennia, organisms that sprang back to life when thawed. If Mars' permafrost holds similar survivors, it could rewrite everything we know about life's tenacity. The parallels to Earth are uncanny. In the Arctic, permafrost preserves not just microbes, but entire ecosystems, ancient plant roots, prehistoric viruses, even the remains of woolly mammoths. Mars' version might lack mammoths, but the principle is the same. Ice acts as a preservative, slowing chemical reactions to a crawl and shielding organic material from radiation. The difference: Earth's permafrost occasionally thaws, offering organisms a chance to revive. On Mars, the freeze is permanent, or so we think. Some models suggest that during periods of increased axial tilt, Mars' mid-latitudes might have warmed just enough to let the permafrost's upper layers melt temporarily, creating fleeting pockets of liquid water. For any microbes trapped inside, these brief reprieves could have been lifelines, moments to metabolize, replicate, or repair cellular damage before the cold returned. What's tantalizing is how accessible this icy archive might be. While Mars' polar ice caps are buried under thick layers of dry ice and dust, Arcadia's permafrost lies closer to the surface, in some places just a few meters down. That makes it a prime target for future drills. Imagine a robotic arm piercing the frozen soil, extracting a core sample that hasn't seen sunlight for 3 billion years. Even if no living cells survived, the ice could contain molecular fossils, lipids, proteins, or genetic fragments hinting at organisms that once thrived here. Or it might reveal something stranger: microbes adapted to a cycle of sporadic activity, hibernating for eons between brief awakenings. Yet the permafrost poses a paradox. While it preserves, it also isolates. On Earth, permafrost microbes are part of a larger biosphere, connected to active ecosystems. On Mars, any organisms trapped in the ice would have been cut off, their world shrinking as the planet's surface grew hostile. Could life endure in such solitude? The answer might lie in Earth's own extremes. In Antarctica's dry valleys, microbes exist in ice-cemented soil so arid and cold it's considered the closest terrestrial analog to Mars. They don't thrive, they persist, metabolizing at rates so slow they're almost undetectable. If Martian life followed a similar strategy, Arcadia's permafrost could be less a graveyard and more a suspended animation chamber. The real challenge is contamination. Any mission drilling here would have to be surgically clean, ensuring Earth microbes don't hitch a ride and muddy the results. It's a technical hurdle, but the payoff could be historic. Finding even a single fossilized cell in Arcadia's ice would prove life isn't confined to Earth. And if by some miracle something survived, that would mean life, against all odds, found a way to outlast a planet's death. As we study these frozen plains from orbit, their quiet surface belies the potential beneath, a vault of cosmic secrets, waiting for the right tool, the right moment to crack it open. Nochi's Terra's crater lakes didn't just vanish once, they pulsed in and out of existence like a slow, planetary heartbeat. Picture this: a shallow lake filling a meteor crater during Mars' wetter periods, its waters reflecting the sky before shrinking under the relentless sun, leaving behind cracked mud and evaporite salts. Then, centuries or millennia later, another shift in climate, a tilt of the planet's axis, a burst of volcanic activity, and the basin fills again. This wasn't a one-time event. These lakes cycled through wet and dry phases for millions of years, creating a rhythm of abundance and scarcity, unlike anything we've seen elsewhere on Mars. For life, this ebb and flow would have been both an opportunity and a gauntlet. On Earth, organisms in ephemeral lakes like Australia's Lake Eyre or Nevada's Plaias have evolved astonishing survival strategies. Brine shrimp lay drought-resistant eggs that hatch when water returns. Tardigrades curl into indestructible tun states, reviving years later. If Mars' no-chise lakes hosted life, it might have developed similar tricks, spores that could wait centuries for the next wet phase, or microbes that shifted metabolisms as their world swung between lake and desert. The stakes would have been high. Each drying period would have winnowed out the less adaptable, pushing survivors to evolve ever more creative ways to endure. The evidence lies in the minerals. Some of no-chise craters bear layers of sulfates and chloride salts that form when water evaporates repeatedly, stacking like pages in a geologic diary. Between these salt layers, scientists have spotted intervals of clay, suggesting quieter periods when freshwater pooled long enough to wash away the brines. This push and pull between harsh and hospitable conditions is exactly the kind of environment that could have driven evolutionary innovation. On Earth, extreme habitats like Chile's Atacama desert force microbes to develop redundant metabolic pathways, allowing them to switch energy sources as conditions change. If Martian life existed here, it might have done the same, becoming a master of reinvention just to survive. Yet even the hardiest organisms have limits. No-chise lakes didn't just dwindle, they vanished for good when Mars' climate tipped past a point of no return. Any life adapted to cyclical droughts would have faced a cruel paradox. Its very survival strategies might have made it vulnerable to permanence. Spores waiting for rain that never came, microbes tuned to rhythms that suddenly stopped. It's a haunting thought, life persisting through countless dry phases, only to meet its end when the cycles themselves ceased. The legacy of these lakes isn't just in their fossils, it's in the question they force us to confront. How much change can life withstand before resilience isn't enough? No-chise Terra's ghostly shorelines hold the answer, etched in salt and stone. And as we study them, we're not just learning about Mars, we're uncovering the universal limits of survival itself. Nili Fossae isn't just another crack in Mars' surface. It's a sprawling network of fractures where groundwater might have once bubbled up, creating fleeting oases in an increasingly arid world. Picture this, deep fissures in the rusty rock, their walls lined with shimmering clays and carbonates minerals that only form when water lingers for long stretches. These fractures could have acted like natural plumbing, channeling underground water to the surface in seeps and springs. On Earth, places like Oman's Wadi Shab or Arizona's Havasu Canyon show how oases transform barren landscapes into pockets of life, where even the smallest trickle of water can sustain lush vegetation and diverse wildlife. If Mars had its own version, these oases wouldn't have been just geological quirks, they could have been the last refuges for any life clinging to a dying planet. What makes Nili Fossae so compelling is its chemistry. The region is one of the richest deposits of clays and carbonates ever found on Mars, minerals that act like sponges, trapping and preserving organic material. On Earth, similar clays in places like Greenland's Isua Formation have been found to hold traces of ancient microbes, their molecular fingerprints locked in the rock for billions of years. But here's the twist, Nili Fossae's minerals didn't just form in standing water. Their unique composition suggests they were shaped by groundwater percolating through fractures, meaning these oases weren't fed by rain or rivers, but by hidden reservoirs deep below. For any organisms struggling to survive as Mars dried up, these seepages could have been lifelines, offering stability long after surface water vanished. Yet the story of these oases isn't just about water, it's about energy. On Earth, groundwater-fed springs often host chemosynthetic life, microbes that thrive not on sunlight, but on chemical reactions between water and rock. In places like Ethiopia's Dalol hot springs or Mexico's Cave of Crystals, these organisms turn minerals into fuel, creating entire ecosystems in total darkness. If Mars oases functioned similarly, they might have harbored microbes that lived off reactions between the groundwater and iron or sulfur in the surrounding rock. The fractures themselves could have acted like natural bioreactors, concentrating nutrients and providing sheltered niches where life could persist even as the planet's surface turned to dust. But how long could such refuges last? Unlike Earth's oases, which are replenished by rainfall or snowmelt, Nili Fossi's springs would have depended on dwindling underground reserves. As Mars' interior cooled, the aquifers feeding them would have dried up or frozen, leaving behind only mineral stains as tombstones. That raises a haunting question. Did life here face a slow suffocation, its habitat shrinking until the last spring fell silent? Or did it find a way to retreat deeper, following the water down into the cracks, surviving in isolated pockets beyond our reach? The answer might lie in the fractures themselves. Future missions could drill into these clay-rich veins, searching for microscopic tunnels where biofilms might have grown, or isotopic signatures that hint at ancient metabolic activity. Even if no fossils remain, the minerals could still betray traces of past chemistry imbalances that shouldn't exist without biology's hand. Nili Fossi's oases are more than geological relics. They're a test of life's ability to exploit even the slimmest opportunities, and a reminder that the line between survival and extinction is often drawn by something as simple as a crack in the rock. Terra Cyanum's cracked, salt-crusted plains tell a story of thirst of lakes that grew ever saltier as they shrank under a relentless Martian sky. These aren't just ordinary dry lakebeds. The region's evaporite deposits, minerals like gypsum and halite that crystallize when water vanishes, are chemical diaries of a world slowly losing its liquid lifeline. On Earth, from the Dead Sea to Chile's Atacama, these hypersaline environments are far from barren. They're bustling microbial metropolises where salt-loving extremophiles turn briny pools into vibrant ecosystems. If Mars evaporites hosted similar life, their remains might still be locked in those crystalline lattices, preserved with astonishing fidelity. The magic of evaporites lies in their chemistry. As water evaporates, it leaves behind not just salts, but whatever was dissolved in it, including organic molecules. On Earth, the salt flats of Bolivia's Salar de Uyuni have been found to trap DNA fragments and lipids for millennia. Mars evaporites, formed under similar conditions but untouched by erosion or plate tectonics, could be even better time capsules. The real jackpot would be finding microbial microfossils encased in salt crystals, like tiny insects in amber. But even without intact cells, the minerals might hold biosignatures, chemical imbalances, isotopic quirks, or patterns that scream biology to a trained eye. Yet Terra Cyanum's evaporites pose a paradox. While salt preserves, it also challenges life. The same brines that might have sheltered microbes would have grown lethally concentrated as water vanished. On Earth, organisms in places like Ethiopia's Danakil Depression cope by producing special proteins to balance internal salinity or forming protective biofilms. If Martian life existed here, it would have faced the same brutal arms race, adapting to ever saltier waters until perhaps even the hardiest survivors hit a wall. The evaporites layers might capture that struggle, with younger deposits showing fewer signs of life as conditions grew unbearable. What's haunting is how these lakes met their end. Unlike Earth's salt flats, which often refill seasonally, Terra Cyanum's evaporites likely mark the last gasp of a dying hydrological cycle. The final layers might be pure salt, no clays, no organics, just crystalline tombs where the last brine pools flickered out. But between those layers, there could be whispers of what came before. Future missions might use spectrometers to map organic hotspots or drills to extract salt cores for microscopic analysis. Even a single chain of lipids or a strange carbon isotope ratio could rewrite history. The lesson of Terra Cyanum isn't just about Mars, it's about life's dance with scarcity. Evaporites are nature's hourglasses, measuring how long biology can cling to a shrinking resource. If life thrived here before vanishing, it's a cautionary tale. If it found a way to persist, it's a revelation. Either way, these salt-stained plains are more than geological relics. They're the universe's way of asking how far life will go when the water runs out. Gusev crater might look like just another windswept basin on Mars, but beneath its dust lies a secret, ghostly remnants of what could have been ancient hot springs. When NASA's Spirit rover rolled across this region, its wheels kicked up something extraordinary: patches of nearly pure silica, so bright they gleamed like shattered glass under the Martian sun. On Earth, deposits like these only form in two places: steamy volcanic vents and bubbling hot springs. And where there are hot springs, there's often life. Picture a Martian spring, steam curling from cracks in the rock, mineral-rich water cascading over terraces, leaving behind siliceous layers that hardened over millennia. If Earth's Yellowstone is any guide, these would have been prime real estate for microbes, their colonies forming slimy mats that fossilized into stone as the waters dried up. The parallels are impossible to ignore. In places like Chile's El Teitio geyser field or Iceland's H. Verivelia, silica deposits preserve microbes with stunning detail, turning living mats into literal rock records. These fossils, called stromatolites, are some of Earth's oldest evidence of life, dating back 3.5 billion years. If Gusev Springs hosted similar organisms, their remnants might still be there, locked in those glittering silica veins. The challenge: Mars hasn't been kind to its rocks. Billions of years of radiation, dust storms, and temperature swings could have erased delicate cellular structures. But silica is stubborn. On Earth, it's been known to preserve even the finest microbial textures, individual filaments, cell clusters, even the sticky biofilms that held mats together. If Martian microbes existed, their silica tombs might have shielded them from the worst of Mars erosion, leaving behind whispers of biology frozen in stone. Yet the story of Gusev Springs isn't just about preservation, it's about energy. Hot springs aren't passive puddles, they're dynamic systems where geology and biology collide. On Earth, hydrothermal microbes thrive on chemical gradients, feeding off reactions between water and minerals like iron or sulfur. In Gusev, where the silica deposits mingle with sulfate salts, any ancient organisms would have had a similar buffet. But here's the twist: Mars springs wouldn't have lasted forever. As the planet's volcanic activity waned, the heat source fueling these oases would have faded. The waters would have cooled, then vanished, leaving behind only crystallized remnants. For any life depending on them, it would have been a slow suffocation, a retreat into dormancy as their world turned to stone. The haunting question isn't just whether life existed here, but how far it got before the lights went out. Did Gusev's springs host simple, solitary microbes, or did they foster complex communities with species specialized for different niches along the spring's temperature gradient? On Earth, hot spring ecosystems can be surprisingly diverse, with organisms adapted to scalding vents, tepid pools, or even the damp edges where steam condenses. If Mars followed a similar script, its fossils might reveal a biosphere more sophisticated than we've dared imagine. Future missions could hold the key. A rover equipped with a high-resolution microscope might scan Gusev's silica for microfossils, hunting for telltale textures like those in Earth's ancient rocks. Even without intact cells, chemical signatures like carbon isotopes skewed by metabolism could hint at past biology. Until then, Gusev's silent springs remain a tantalizing maybe, a place where the universe might have tried just once to write life's story in stone. And if it did, those glittering silica patches aren't just geological curiosities. They're pages in a book we're only beginning to read. Ares Valleys isn't just a scar left by ancient floods. It's a testament to the chaos and creativity of water on Mars. Picture this: torrents of water, unleashed by ruptured aquifers or melting glaciers, thundering across the landscape with enough force to carve channels deeper than the Grand Canyon. But between these cataclysmic events, something quieter may have taken hold. As the floodwaters receded, they could have left behind patches of sodden ground, shallow ponds, and meandering streams, a network of transient wetlands clinging to the edges of the devastation. On Earth, wetlands are biodiversity hotspots, places where life thrives in the delicate balance between water and land. If Mars had its own version, even for fleeting moments, these muddy margins could have been the closest thing to a nursery for extraterrestrial life. What makes wetlands so special isn't just their water, it's their chemistry. Stagnant pools rich in decaying organic matter become factories for complex molecules, while shifting water levels create microenvironments where different species can carve out niches. On Earth, from the Everglades to the Okavango Delta, wetlands teem with microbes, plants, and animals adapted to the ebb and flow. Mars' version would have been far simpler, but the principle remains: where water lingers, life finds a way. The clues lie in Ares Valley sediments. Orbital scans reveal layered deposits of clays and sulfates, minerals that form in quiet water. Some patches even show ripples, fossilized waves from shallow ponds that stood long enough for winds to stir their surfaces. These aren't just relics of floods, they're snapshots of the calm between storms. Yet the odds were stacked against any would-be Martian microbes. Wetlands on Earth persist for centuries, sustained by rain and groundwater. On Mars, these oases would have been ephemeral, drying up within years or decades as the planet's thin air stole their moisture. Survival would have demanded a strategy as brutal as the environment: rapid reproduction, drought-resistant spores, or the ability to lie dormant for millennia between wet periods. Extremophiles on Earth offer glimpses of how this might work. In Chile's Atacama Desert, microbes spring to life after rare rains, only to retreat into suspended animation when the water vanishes. If Martian life existed, it might have followed a similar rhythm, blooming in the mudflats of Ares Valleys, then vanishing like a mirage when the waters retreated. The real mystery isn't just whether life could have existed here, but how far it could have evolved in these short-lived havens. Wetlands are crucibles of innovation. On Earth, they're where fish first crawled onto land, where plants evolved complex roots. Mars wetlands wouldn't have had time for such leaps, but they might have allowed simple organisms to experiment with survival strategies. Perhaps some developed ways to harness trace gases like methane or hydrogen, or learn to weave protective biofilms as the ground cracked beneath them. The haunting possibility is that these wetlands weren't just brief respites, they were testing grounds, where life was given a fleeting chance to prove its resilience before the planet's climate pulled the plug. Future missions could unlock these secrets. A rover equipped with a drill might sample Ares Valley's mudstone layers, hunting for microscopic tunnels left by biofilms or chemical traces of metabolic activity. Even if no fossils remain, the very structure of the sediments could betray signs of biological tinkering, clay particles aligned by sticky microbial mats, or mineral concentrations that defy abiotic explanation. Until then, Ares Valley stands as a monument to life's audacity, a place where the universe whispered, "Try," before Mars answered, "No." But in that whisper lies a revelation. Even the briefest window of habitability can be enough for life to write its name in the mud. Rising like frozen titans above Mars' Tharsis bulge, the volcanoes of Olympus Mons and its neighbors held more than just fire in their past, they may have cradled ice. Picture these towering peaks not as the barren slopes we see today, but as frost-capped giants, their summits glazed with glaciers that fed trickling meltwater streams down their flanks. On Earth, from the Andes to Iceland, volcanic ice melts create ephemeral oases, pools where steam meets snow, and microbes thrive in the narrow zone between heat and cold. If Mars' volcanoes once wore icy crowns, their thawing edges could have been the perfect stage for life's delicate dance between survival and extinction. The mechanics are strikingly Earth-like. When geothermal heat meets ice, it doesn't just create water, it builds ecosystems. Consider Iceland's Vatnajökull, where subglacial volcanoes melt overlying ice, forming temporary lakes teeming with extremophiles. These organisms don't need sunlight, they feast on minerals liberated by the melt. On Mars, even a trickle of meltwater from Tharsis icy caps could have carved channels through volcanic soil, creating mineral-rich rivulets where hypothetical microbes might have flourished. The evidence is etched into the planet's surface, gullies radiating from some volcanic regions, resembling the runoff patterns seen on Earth's glacier-covered volcanoes. Unlike flash floods that rage and vanish, these would have been slow, seasonal seeps, offering stable habitats for years or decades before freezing over again. Yet Mars' version of this cycle would have been far more precarious. Without Earth's thick atmosphere to regulate temperatures, the line between liquid and frozen was razor thin. A single cold spell could have locked these habitats away for centuries. Any organisms here would have faced a brutal paradox: too close to the volcano and they'd cook, too far and they'd freeze. Survival would have demanded a Goldilocks strategy, migrating with the melt line, or developing spores tough enough to wait out the freeze. On Earth, bacteria like Chrysobacterium greenlandensis have been revived from ice cores after 120,000 years. If Martian life existed, Tharsis' icy flanks might have been its ultimate test, a game of biological hide and seek with planetary climate as the referee. The real intrigue lies in the chemistry. Volcanic terrains are mineral buffets offering sulfur, iron, and silica, ingredients that Earth's extremophiles transform into energy. Mars' Tharsis region is laced with sulfate deposits, suggesting water once interacted deeply with volcanic rock. But here's the twist: these minerals could have acted as both life-givers and life-takers. Sulfates might have fed early microbes, but as water evaporated, concentrated brines could have turned toxic. The fossil record, if any exists here, might capture that struggle, layers showing microbial adaptations to increasing salinity until finally the salts overwhelm them. What makes Tharsis' icy volcanoes so compelling isn't just their past potential, it's their lingering mystery. Unlike dried lakebeds or flood channels, these habitats would have been patchy and transient, leaving fewer obvious traces. Future missions might target their faint mineral stains or probe for isotopic signatures in volcanic soils. Until then, these icy peaks stand as silent sentinels, guarding answers to whether life ever danced on the knife's edge between fire and frost, and if so, how long it could keep its balance before the music stopped. Beneath the looming shadow of Pavanus Mons, Mars hides one of its most intriguing possibilities, a labyrinth of subsurface caverns carved by ancient lava flows. These aren't just empty tunnels. Picture vast, winding chambers where volcanic gases once mingled with trapped water vapor, creating microclimates that might have lingered long after the planet's surface turned to dust. On Earth, from Hawaii's Thurston lava tube to Spain's Cueva de los Verdes, such caves are more than geological curiosities, they're sanctuaries for life. Blind insects, translucent crustaceans, and bacteria that feed on rock thrive in these sunless worlds. If Mars' lava tubes held even a fraction of this potential, they could have been the ultimate refuge for any organisms struggling to survive a dying planet. What makes these caverns so special is their insulation. While Mars' surface baked under radiation and froze in the thin air, underground chambers would have offered stability, steady temperatures, protection from cosmic rays, and possibly even lingering humidity from trapped ice or geothermal vents. The chemistry gets even more intriguing. Lava tubes often contain iron-rich minerals like olivine, which react with water to produce hydrogen, a potential energy source for microbes. On Earth, we've found entire ecosystems in South Africa's gold mines that run on this exact process, with bacteria turning rock and hydrogen into life-sustaining chemical reactions. If Martian organisms existed, they might have discovered the same survival manual, thriving in the damp darkness beneath Pavanus Mons. Yet the real mystery isn't just whether life could have existed here, it's how long it could have lasted. Lava tubes aren't eternal. As Mars' volcanic activity waned, so would the heat that kept some caverns above freezing. Any ice would have slowly sublimated, and trapped gases would have leaked away. But here's the twist. Some models suggest these caves might still hold pockets of humidity today, their walls beading with condensation during warmer seasons. That raises a tantalizing question. Could anything have adapted to this slow-motion exodus, following the water deeper into the rock as conditions worsened? On Earth, we've found microbes living in pores within solid rock, surviving on traces of moisture and mineral reactions. If Martian life was equally tenacious, its descendants might still be there, hidden in cracks too small for rovers to see. The search for answers might lie in the caverns, skylights, collapsed sections where the roof caved in, offering a glimpse into the darkness below. Orbiters have spotted dozens of these openings around Pavanus Mons, some large enough to swallow a city block. Future missions could lower probes into these pits, sampling the air for whiffs of methane or other gases that might hint at active chemistry or even biology. Even without direct exploration, mineral stains around these openings could tell a story. On Earth, cave entrances often accumulate unique minerals like manganese oxides, which sometimes form with microbial assistance. Finding similar deposits on Mars would be like discovering a faded, welcome sign at life's last outpost. Pavanus Mons' hidden world is more than a geological footnote. It's a test of life's ability to retreat, adapt, and persist in the unlikeliest corners. These caverns might hold the final chapter of Mars' biological story, whether it's a tale of quiet extinction or a revelation that life, once rooted, refuses to let go. As we peer into those shadowed openings from orbit, we're not just staring at empty tunnels. We're looking at the universe's ultimate hide-and-seek game, waiting for the day we can whisper, "Found you." Morth Valleys doesn't just cut through Mars' surface. It hides layers of clay so finely stacked, they read like a geological love letter to water. but these aren't just any clays. Their chemistry suggests something extraordinary, an ancient estuary where freshwater rivers met salty basins in a slow, rhythmic dance. On Earth, from the Chesapeake Bay to the Amazon Delta, estuaries are biological powerhouses, nurseries where nutrients collide, currents mix, and life thrives in the constant push and pull between two worlds. If Mars ever hosted its own version, this winding valley could have been a cradle for extraterrestrial life, a place where microscopic pioneers exploited the gradient between salt and fresh, building ecosystems in the brackish swirl. The magic lies in the clays themselves. Morth Valley's deposits are rich in smectite and montmorillonite minerals that form when water lingers, altering volcanic rock over millennia. But what's revelatory is their layering. Some bands are aluminum-rich, hinting at prolonged weathering by freshwater. Others are iron-heavy, suggesting briny pools that evaporated under Mars' thinning sky. This alternating pattern mirrors Earth's estuaries, where tides and river flows create zones of varying salinity, each hosting specialized microbes. In places like Georgia's Altamaha River estuary, scientists find bacteria adapted to precise salt concentrations, some so finely tuned they perish if levels shift by even a few percent. If Morth Valley's waters once mixed in similar ways, its clays could preserve the fossilized remnants of organisms that mastered this delicate balance. Yet Mars' estuaries would have faced a challenge Earth's never do: instability. Without a massive moon to stabilize its tilt, Mars' climate wobbled wildly, swinging between extremes. An estuary that thrived for centuries might have dried up within decades, its waters retreating or freezing as the planet's axis shifted. Life here would have needed a survival strategy as flexible as the environment, perhaps microbes that could switch metabolisms as salinity fluctuated, or form drought-resistant biofilms when waters vanished. Earth offers glimpses of how this might work. In Australia's Shark Bay, stromatolites endure in hypersaline lagoons by trapping moisture in their layered mats. If Martian microbes employed similar tricks, their fossilized remains might still lurk in Morth Valley's clay strata, their microscopic architectures preserved like pressed flowers in a book. The real intrigue isn't just whether life existed, it's how far it could have evolved in these fleeting brackish zones. Estuaries are evolutionary accelerators. On Earth, they're where fish develop tolerance to salinity shifts, paving the way for marine life to colonize rivers. Mars' version wouldn't have had time for such leaps, but it might have spurred microbial innovation. Imagine organisms evolving pigments to harness faint sunlight through muddy waters, or enzymes to process both sulfur and iron as oxygen levels crashed. The clays could hold echoes of these experiments, their chemistry skewed by ancient metabolic processes. Future missions might decode this puzzle. Morth Valleys was once a finalist for a rover landing, and for good reason. Its layers are exposed like pages in a book, ripe for drilling. A spectrometer could detect organic residues trapped between clay sheets, while a high-resolution microscope might spot fossilized microbial mats. Even if the search proves futile, the absence would be revealing. A sterile Morth Valleys would suggest that mixing water alone isn't enough, that life demands stability Mars couldn't provide. But if the clays whisper back, their message could reshape our cosmic perspective, proving that where waters merge, life might too. Meridiani Planum's cracked, sun-baked surface hides more than just vast salt flats. It conceals the ghostly outlines of ancient playa lakes, shallow depressions that filled with water for just weeks or months before vanishing under the relentless Martian sun. These weren't permanent lakes or raging rivers. They were fleeting oases bubbling up after rare rains or groundwater seepage, only to evaporate into the thin air, leaving behind nothing but mineral stains and mud cracks. On Earth, from Nevada's Black Rock Desert to Bolivia's Salar de Uyuni, Planitia are anything but dead zones. They're stages for some of life's most audacious adaptations: shrimp eggs that wait decades for rain, microbes that thrive in brine 10 times saltier than the ocean. If Mars' Planitia ever hosted life, it would have needed to master the art of existing on borrowed time. The evidence lies in the textures. Meridiani's rocks bear the unmistakable marks of repeated wetting and drying polygonal cracks that form when mud shrinks, layers of sulfate salts that crystallized as waters evaporated. But what's fascinating is the scale. Some deposits suggest these Planitia weren't isolated puddles. They could have spanned kilometers, forming interconnected networks during wetter periods. Picture a Martian summer where a single storm transforms the plain into a shimmering, if temporary, wetland. For organisms adapted to boom and bust cycles, these fleeting waters might have been enough. On Earth, creatures like fairy shrimp hatch, grow, and lay eggs in Planitia lakes that last mere weeks. Their strategy, speed, and resilience. If Martian life existed here, it might have followed a similar playbook: explosive growth during wet phases, followed by dormancy when the waters vanished. Yet Mars' Planitia pose challenges Earth's never face. Without a thick atmosphere to buffer temperature swings, these lakes would have boiled by day and frozen by night. Salinity would have skyrocketed as water evaporated, turning brines lethal within days. Any organisms here would have needed to tolerate extremes that would obliterate most earthly extremophiles. But there's a tantalizing possibility. What if life didn't just endure these conditions, it exploited them? In Chile's Atacama Desert, microbes use salt crystals as micro-greenhouses, trapping humidity and UV-blocking shades. Martian microbes might have done the same, turning their own harsh environment into a survival toolkit. The Planitia salts could have acted as both preservatives and traps, sealing away organic molecules like insects in amber. The real mystery isn't just whether life existed here, it's how we'd recognize its traces. Planitia are paradoxes. They preserve, but they also destroy. On Earth, their layers hold fossilized algae mats and insect tracks, but Mars' version has been bombarded by radiation for eons. Any biosignatures would be fragmented, scrambled by time. Yet there's hope. When Opportunity rover analyzed Meridiani's soils, it found tiny hematite spheres nicknamed blueberries, concretions that often form in water-rich environments on Earth, sometimes with microbial assistance. Were these just geological quirks, or could they hint at something more? Future missions might settle the debate by scanning Planitia sediments for molecular patterns, lipid remnants, isotopic fingerprints, or even the faintest traces of genetic material frozen in salt. What makes these vanished Planitia so compelling isn't their size or longevity, it's their audacity. They represent life's potential to carve out a foothold in the most ephemeral of habitats. A Planitia lake might last only a season, but for a microbe, that's an eternity. As we study Meridiani's cracked plains, we're not just looking for fossils. We're asking whether the universe's recipe for life includes a line we've barely considered. Not just water, but the ability to wait. Cerberus Fossae isn't just a series of cracks on Mars, it's the scar of a planetary fever dream, a place where the ground itself might have once bled water instead of lava. Imagine a landscape where geysers of briny slush erupt from fissures, their plumes freezing instantly in the thin air, dusting the plains with glittering ice crystals. These aren't your typical volcanoes. They're cryovolcanos, rare and mysterious features that spew water, ammonia, or methane, a phenomenon we've seen on icy moons like Enceladus and Europa, but one that could have reshaped Mars' fate. If Cerberus Fossae was once alive with these icy eruptions, it might have been the planet's last gasp at sustaining liquid water, and with it, any lingering life. The mechanics are both elegant and brutal. On Earth, volcanoes tap into molten rock, but volcanoes draw from subterranean reservoirs of liquid water kept from freezing by heat from the planet's core or tidal friction. When pressure builds, the water bursts through the surface, flash freezing into plumes or flowing as viscous slurries before evaporating into the arid air. On Mars, Cerberus Fossae's long, linear fractures, some stretching hundreds of kilometers, are textbook candidates for this activity. Orbital images show features resembling frozen flows, their surfaces oddly smooth compared to the surrounding terrain, as if something once oozed across them before time locked them in place. These could be the remnants of cryovolcanic eruptions, Mars' equivalent of Yellowstone's geysers, but with water instead of steam. What's haunting is the timing. Cerberus Fossae's fractures are geologically young by Martian standards at least. Some estimates suggest they formed within the last few million years, a blink of an eye in planetary terms. That raises a spine-tingling possibility. While most of Mars' water vanished billions of years ago, cryovolcanoes here might have offered fleeting respites, episodic bursts of liquid in an otherwise terminally dry world. For any subsurface life clinging to existence, these eruptions could have been lifelines, delivering both water and heat to otherwise frozen depths. On Earth, we've found microbes thriving in the dark, heated waters of subglacial volcanoes like Iceland's Grimsvötn. If Mars had its own version, these icy eruptions might have been its final act of biological hospitality. Yet the story of Cerberus Fossae isn't just about water, it's about energy. Cryovolcanoes don't just spit out liquid, they bring up minerals and gases from deep underground. On Saturn's moon Enceladus, cryovolcanic plumes contain hydrogen, methane, and even organic molecules, a buffet for potential life. If Mars' cryovolcanoes were similarly generous, their eruptions could have seeded the surface with chemical building blocks, creating temporary oases where microbes might have flourished. The irony, these same eruptions could have accelerated Mars' demise. Every burst of water would have evaporated quickly, its molecules stripped away by solar winds, further depleting the planet's dwindling reserves. Cryovolcanoes might have been both lifeboat and executioner, offering brief salvation while hastening the end. The ultimate question isn't just whether these icy volcanoes existed, it's why they fell silent. On icy moons, cryovolcanism persists because of gravitational flexing from nearby planets. Mars, lacking such a dance partner, relied solely on its internal heat, which faded as the planet's core cooled. Without that energy, the water reservoirs feeding the cryovolcanoes would have frozen solid, turning Cerberus Fossae from a dynamic landscape into a frozen graveyard. That transition might hold the key to understanding life's limits. If organisms here adapted to sporadic eruptions, their extinction wouldn't have been sudden. It would have been a slow suffocation, a waiting game they ultimately lost. Future missions could rewrite this narrative. A probe equipped with ground-penetrating radar might detect buried ice layers or ancient plumbing systems beneath Cerberus Fossae's fractures. Even more compelling would be catching a whiff of methane or hydrogen sulfide gases that, on Earth, often signal microbial activity in geothermal zones. Until then, these fissures remain frozen question marks, their silence a reminder of how close Mars might have come to cheating death and how brutally the universe enforces its rules. A city's Planitia sprawls across Mars' northern lowlands like a vast, silent wetland frozen in time but peer closer, and the basin's mineral stains tell a different story. This isn't just another dry lakebed. The clays and sulfates here bear the chemical signature of brackish water. a delicate balance between fresh and salt, where rivers might have mingled with briny groundwater to create marshes unlike anywhere else on the planet. Picture a Martian wetland, shallow pools tinged rusty red with dissolved iron, their edges crusted with salts that glint under a pale sun. On Earth, from the Everglades to the Okavango Delta, such brackish zones are teeming with life, microbes that toggle between salt and fresh, plants with specialized salt-filtering roots, even fish that migrate between the two. If Mars' marshes ever hosted organisms, they would have faced a ruthless evolutionary crucible: adapt or perish with every shift in salinity. The key lies in acids' layered deposits. Orbital spectrometers reveal smectite clays, minerals that form in slow-moving water, interleaved with sulfate salts like gypsum, which crystallize when brines evaporate. This alternating pattern mirrors Earth's coastal marshes, where tides and river flows create a patchwork of microhabitats. In Maryland's Chesapeake Bay, for example, bacteria living just centimeters apart employ entirely different metabolisms depending on whether they're bathed in freshwater seepage or saltwater surges. Mars' version would have been simpler but no less dynamic. A single storm could have diluted pools near river inlets, while evaporation concentrated others into hypersaline pockets, a mosaic of challenges for any would-be organisms. What's haunting is how these marshes might have met their end. Unlike Earth's wetlands sustained by rain and groundwater, Acidi's water likely came from sporadic bursts, melting permafrost perhaps, or the last gasps of aquifers. As Mars dried, the marshes would have shrunk, their waters growing ever saltier until even the hardiest survivors hit a wall. On Earth, we see this in places like Utah's Great Salt Lake, where microbial mats turn white with crystallized salts as waters recede. But here's the twist: salt isn't always a death sentence. In Chile's Salar de Atacama, bacteria survive inside tiny brine droplets trapped within salt crystals, essentially carrying their own miniature habitats. If Martian microbes evolved similar tricks, their molecular echoes might still linger in Acidi's salty clays, waiting for a rover's drill to uncover them. The real question isn't just whether life existed here, it's how far it could have innovated. Brackish zones are evolutionary pressure cookers. In the Baltic Sea, where freshwater rivers meet the ocean, organisms have developed proteins that change shape to cope with shifting salinity. If Mars' marshes lasted long enough, their inhabitants might have pioneered equally creative solutions, perhaps enzymes that worked across salt gradients, or cell membranes that reconfigured like molecular origami. Future missions could search for these adaptations in the basin's minerals, hunting for isotopic anomalies or organic molecules that defy non-biological explanations. Acidi's Planitia's silent marshes are more than a geological curiosity. They're a test of life's ability to navigate the universe's subtlest edges, the spaces between fresh and salt, wet and dry, survival and oblivion. As we map their long-vanished shores, we're not just studying Mars. We're learning how thin the line between a living world and a dead one can be, and how tenaciously life might cling to that line before letting go. Deuteronomus Menzies' jagged terrain looks like a page torn from Earth's polar atlas: towering cliffs, U-shaped valleys, and deep, winding channels that could pass for Norway's fjords if not for the rust-colored dust. But these aren't just geological doppelgangers. They're relics of a time when glaciers might have carved through Mars' highlands, grinding rock into powder and leaving behind meltwater lakes in their wake. Imagine standing on the edge of one of these ancient fjords, gazing down at a turquoise lake fed by icy waterfalls, its surface dotted with icebergs calving from glaciers above. This isn't just scenic speculation. The physics of ice and gravity work the same everywhere in the universe. If glaciers existed here, they would have melted at their edges, creating exactly these kinds of ephemeral oases, pockets of liquid water clinging to the margins of a frozen world. What makes these fjords so compelling is their duality. On Earth, glacial meltwater lakes are biological hotspots. In Greenland's Disco Bay, algae bloom where ice meets water, feeding entire food chains. The meltwater itself is far from sterile. It's laced with minerals scraped from bedrock, creating a nutrient-rich soup. If Deuteronomus menzies fjords harbored similar lakes, they could have been crucibles for life, however simple. The chemistry lines up. Orbital data shows clays and sulfates here, minerals that form when water interacts with rock over time. But there's a twist. Mars' fjords would have been lonelier than Earth's. Without tides or seasons as consistent as ours, their lakes might have been stagnant, freezing over entirely during colder spells. Any organisms here would have faced a boom and bust, existence thriving in brief thaws before retreating into dormancy when the ice returned. The real intrigue lies in the ice itself. On Earth, glaciers preserve ancient life. In Antarctica, scientists have revived microbes trapped in ice for millions of years. If Mars' fjords held glaciers, their layers might still entomb frozen specimens of whatever clung to their edges. The challenge: these glaciers wouldn't have behaved like Earth's. Mars' lower gravity and thinner atmosphere would have made them flow slower, melt differently, and fracture in unexpected ways. Picture a glacier oozing like cold honey, its meltwater seeping through cracks rather than gushing in streams. Any lakes it fed would have been transient, perhaps lasting only decades before vanishing. For life, that's an evolutionary tightrope: adapt to exploit fleeting opportunities or perish. Yet even short-lived fjord lakes could have left clues. If microbial mats grew along their shores, they might have left behind layered deposits akin to Earth's stromatolites. If meltwater carried iron or sulfur into the lakes, chemical reactions could have created minerals with distinct isotopic fingerprints, hints of biological tinkering. Future missions might target these fjords' exposed sediments, scanning for textures or chemistry that defy abiotic explanations. The absence of such signs would be equally revealing, suggesting that even with water and time, some worlds never cross the threshold from geology to biology. Deuteronomus menzies fjords are more than icy ghosts. They're a test of life's ability to exploit the narrowest windows of opportunity. A reminder that habitability isn't just about having water, but about timing. As we map their dry valleys from orbit, we're not just studying Mars' past. We're asking whether life, when given a foothold, can endure even when its refuge is as fleeting as meltwater in the wind. Olympia Undine's sweeping dunes might look like a desert frozen in time, but hidden between their crests lies evidence of something far more surprising: vanished wetlands that once turned the spaces between dunes into temporary oases. Picture this: towering sand hills, their slopes darkened by dampness, with shallow pools glistening in the hollows where winds couldn't reach. These weren't permanent lakes or raging rivers. They were fleeting pockets of moisture, fed by groundwater seeping up through the sand or melting frost clinging to the dunes' shadows. On Earth, from Namibia's Namib Desert to Saudi Arabia's Empty Quarter, these interdune wetlands are biological treasure troves, microscopic worlds where bacteria and algae thrive in the thin film between sand and water. If Mars' dunes ever held similar damp refuges, even for a season, they could have been the stage for extraterrestrial life's most delicate performance. The clues are etched into the dunes themselves. Orbital images reveal dark streaks and polygonal cracks along Olympia Undine's slopes, features that, on Earth, only form when sand is damp enough to clump and fracture as it dries. Even more telling are the mineral stains. Spectrometers have detected traces of sulfates and clays in the interdune valleys. compounds that typically form where water lingers long enough to interact with minerals. But here's what's fascinating. These wetlands wouldn't have been static. Like their earthly counterparts, they'd have pulsed with the planet's climate, swelling after rare snowfalls or underground thaw events before vanishing under the sun's glare. For any organisms here, survival would have meant mastering the art of patience, blooming in the dampness, then retreating into dormancy when the sands dried. Earth's interdune wetlands offer a blueprint for how this might have worked. In Chile's Atacama Desert, microbial mats lie dormant for years beneath the sand, only to photosynthesize furiously when fog or rain provides a fleeting window of moisture. Mars' version would have been harsher, shorter wet phases, fiercer UV radiation, and water laced with perchlorates, chemicals toxic to most Earth life. Yet extremophiles here have shown us that life finds workarounds. Some desert microbes use perchlorates as energy sources, turning poison into fuel. Others encase themselves in protective biofilms, essentially building tiny greenhouses in the sand. If Martian microbes existed, Olympia Undi's damp pockets might have been their proving ground, a place to test survival strategies too radical for Earth. The haunting question isn't just whether life could have existed here, it's how we'd recognize its traces. Interdune wetlands are ephemeral by nature. Their organic signatures are often faint, scattered by wind or buried under shifting sands, but there's hope. On Earth, microbial activity in dunes leaves subtle clues, sand grains cemented together by sticky biofilms, or layers enriched in phosphorus and carbon. Mars' weaker weathering might have preserved these fingerprints better than our own planet's restless deserts. Future rovers could sift through Olympia Undi's sands, hunting for aggregates that seem too perfectly clustered, or mineral stains arranged in telltale patterns. Even a single grain of sand coated in organic residue could rewrite our understanding of life's cosmic reach. What makes these vanished wetlands so compelling isn't their size or longevity, it's their audacity. They represent life's potential to exploit the thinnest slivers of habitability, to thrive in places where water is measured in droplets rather than lakes. Olympia Undi's dunes stand as a monument to resilience, their dry slopes whispering of a time when even the spaces between grains of sand might have been enough. Terra Cimeria's cracked, mineral-stained plains hold a secret, a network of ancient alkaline lakes so chemically extreme they would make Earth's Dead Sea seem tame. These weren't your typical Martian water bodies. Picture shallow, briny pools tinged deep blue-green from dissolved carbonates, their edges crusted with jagged towers of precipitated salts like something from an alien dreamscape. On Earth, places like California's Mono Lake or Tanzania's Lake Natron show us just how wild alkaline environments can get. Waters so basic they can burn human skin, yet teeming with specially adapted life. If Mars once hosted similar lakes, their ghostly remains might hold clues to one of astrobiology's biggest questions: how far can life bend before it breaks? The proof lies in the chemistry. Orbital spectrometers have detected thick layers of sodium carbonate and borax across Terra Cimeria minerals that only form when alkaline waters evaporate completely. But what's fascinating isn't just their presence, it's their context. These deposits mingle with clays and silica, suggesting these lakes weren't static death traps. They likely cycled between wet and dry phases, sometimes diluted by rainfall or groundwater, other times concentrating into lethally briny soups. On Earth, such fluctuations create niches for organisms with bizarre survival strategies. At Mono Lake, for instance, bacteria like Bacillus alkaliphilus thrive at pH levels comparable to bleach, while tiny brine shrimp evolve proteins that literally stiffen to protect their cells from the corrosive waters. If Martian microbes existed here, they might have developed equally radical adaptations, perhaps using dissolved metals like magnesium as biological tools, or evolving membranes unlike anything we've seen. Yet Mars' alkaline lakes would have posed unique challenges even Earth's extremophiles never faced. Without an ozone layer, surface waters would have been bombarded by UV radiation, breaking down organic molecules faster than they could form. The lake's high salinity might have prevented freezing, but their chemistry could have been chaotic, shifting unpredictably as carbon dioxide from the thin atmosphere dissolved into the waters, creating unstable carbonate buffering systems. Life here would have needed to be not just hardy, but hyper-flexible, capable of rewriting its metabolic playbook as the lake's pH swung wildly. Earth offers glimpses of how this might work. In Ethiopia's Danakil Depression, microbes switch between sulfur and iron metabolism, depending on which chemicals dominate their ever-changing pools. Martian organisms, if they existed, might have taken this further, perhaps using perchlorate's toxic salts abundant on Mars as emergency energy sources when traditional options vanished. The real intrigue lies in preservation. Alkaline environments are paradoxes. They're harsh enough to kill most life, yet fantastic at preserving its remains. On Earth, Lake Natron's waters have mummified birds and bats so perfectly they seem sculpted from stone. Mars' carbonate deposits could have done the same, fossilizing microbial mats or even individual cells in exquisite detail. Future missions might target these layers with drills, hunting for microscopic textures like those in Earth's alkaline stromatolites, wrinkled layers where biofilms once grew, or tiny bubbles trapped in salt that once housed gas-producing bacteria. Even more tantalizing, some alkaline minerals like trona can preserve DNA-like molecules for millions of years. While Martian life wouldn't have used DNA, finding any complex organic polymer in these salts would be revolutionary. What makes Terra Sumeria's lakes so compelling isn't just their extremity, it's their reminder that life doesn't play by Earth's rules. A microbe that evolved in Martian soda lakes might not even recognize our idea of habitable. Its chemistry could be alien at a molecular level, built around elements we consider toxic or pathways we've never imagined. As we study these vanished lakes from orbit, we're not just looking for life as we know it. We're peering into a mirror that shows us how narrow our definitions might be and how much stranger and more wonderful the universe could be than we've dared to dream. Noctis labyrinthus isn't just a jumble of canyons. It's a fossilized labyrinth where water might have pooled in the most unexpected places. Picture this: after a rare Martian rainstorm or a sudden groundwater seep, shallow ponds glistening on canyon floors, their surfaces reflecting the jagged cliffs above. These weren't vast lakes or raging rivers. They were transient puddles, some no larger than a backyard swimming pool, vanishing within weeks under the sun's glare or seeping back into the fractured rock below. On Earth, from Arizona's desert to Nodges to Australia's claypans, even the briefest pools can burst with life. Fairy shrimp hatching from decades-old eggs, algae blooming in days, microbes colonizing damp cracks. If Mars' fleeting ponds followed the same script, they could have been biological waste stations, offering life a precarious foothold in an increasingly hostile world. What makes these ephemeral ponds so fascinating is their sheer improbability. Noctis labyrinthus sits near the equator, where temperatures swing violently and the air is too thin to hold moisture for long. Yet orbital images reveal telltale mineral stains, sulfates and clays that only form where water lingers, even briefly. Some canyon floors bear polygonal cracks, identical to the patterns seen in Earth's dried mudflats. Others show smooth, rounded pebbles, stones worn by tumbling in shallow currents. These clues suggest that water didn't just appear here. it returned over and over in cycles that could have allowed life to adapt. Think of Earth's desert crustaceans, whose eggs survive years of drought only to hatch within hours of rain. Martian organisms, if they existed, might have mastered a similar rhythm, dormant until dampened, then racing through their life cycles before the water disappeared. The real intrigue lies in the chemistry. Temporary ponds aren't just water, they're concentrated soups of whatever minerals wash in. On Earth, ephemeral pools in places like Chile's Atacama become acidic or alkaline as they evaporate, creating microenvironments where specialized microbes thrive. Mars ponds might have been even more extreme, laced with perchlorates or iron oxides that would poison most Earth life. But extremophiles here have shown us that poison is often just fuel in disguise. Bacteria in California's Mono Lake thrive on arsenic, while others in acidic mine drainage live off dissolved metals. If Martian microbes existed, Nocti's ponds could have been their testing grounds, pushing biochemistry to limits we've barely imagined. Yet the challenge wasn't just surviving, it was reproducing before time ran out. Earth's temporary pond specialists have evolved shortcuts: rapid cell division, spores that scatter on the wind, or eggs that hatch at the first hint of moisture. Mars organisms, if any, would have faced stricter deadlines. With ponds lasting perhaps weeks, generations might have needed to bloom, reproduce, and die within days. The fossil record, if it exists here, would be sparse: a few trapped cells in dried mud or chemical signatures in mineral crusts, but even that would be revolutionary. Finding evidence that life could compress its entire cycle into such fleeting windows would redefine our understanding of biology's resilience. Nocti's labyrinthous ghostly ponds are more than geological footnotes. They're a lesson in how narrow the line between existence and extinction can be. As we study their long, dry beds, we're not just looking for life, we're asking whether a handful of rainy days, scattered across millennia, could ever be enough. Beneath the frozen wasteland of Planum Australe, Mars' south polar ice cap, lies one of the most tantalizing possibilities in our search for extraterrestrial life: hidden rivers of liquid water, flowing silently in the darkness. These aren't just theoretical. Radar data from orbiters has revealed bright reflective patches beneath the ice, signatures that match subglacial lakes on Earth like Antarctica's Lake Vostok. But here's what's astonishing: these Martian reservoirs might not be isolated. Some scientists suggest they could form interconnected networks, subterranean waterways winding beneath miles of ice, shielded from the harsh surface conditions that turned Mars into a freeze-dried desert. The physics at work here is both elegant and alien. On Earth, subglacial water stays liquid thanks to geothermal heat and the immense pressure of overlying ice, which lowers water's freezing point. Mars lacks active volcanoes, but its ice caps are massive, up to 2 miles thick in places, creating enough pressure to keep water liquid even at sub-zero temperatures. Add dissolved salts acting as antifreeze, and you've got a recipe for persistent liquid water in the unlikeliest of places. Picture a dark, slow-moving river under the ice, its waters saturated with perchlorates or sulfates, carving channels through the bedrock over millennia. It's a world untouched by sunlight, where the only energy comes from chemistry and the faint warmth of the planet's core. Yet where there's liquid water, there's potential for life. Earth's subglacial ecosystems are proof. In Antarctica's Blood Falls, iron-rich water seeps from beneath Taylor Glacier, teeming with microbes that have been isolated for millions of years. These organisms don't rely on photosynthesis. They breathe iron and sulfur, turning rock into energy in a process called chemosynthesis. If similar life existed on Mars, Planum Australe's subglacial rivers could have been its last refuge. The parallels are irresistible, a sunless ecosystem cut off from the surface, surviving on chemical reactions between water and rock, but Mars throws in a twist. Without plate tectonics to replenish nutrients, these hypothetical rivers would have been running on a finite supply, their chemistry growing ever stranger as minerals dissolved and concentrated over time. The real enigma isn't just whether life could exist there now, it's how we'd find it. Unlike Earth, where we can drill into subglacial lakes, Mars' ice caps are forbidding. A probe would need to melt through miles of ice, all while avoiding contamination from Earth microbes. Yet the payoff could redefine biology. Discovering life in Mars' subglacial rivers would prove that life can arise independently in radically different environments, suggesting the universe is teeming with it. Alternatively, finding the rivers sterile would force us to ask why. Was the chemistry too extreme? Did Mars' magnetic field collapse too soon? Planum Australe's hidden rivers are more than geological oddities. They're a test of life's universality and its limits. As we stare at radar maps of those mysterious bright spots, we're not just looking at water, we're peering into the darkest, quietest corners of the cosmos, wondering if we're truly alone or if somewhere beneath that ice something is waiting. Ionia Terra's windswept plains might seem barren today, but beneath their dusty surface could lie the echoes of an alien reef, not built by coral but by microbes. Imagine a shallow Martian sea billions of years ago, its sunlit waters teeming with microscopic architects. Layer by layer, these organisms could have stacked themselves into towering structures, their sticky biofilms trapping sediment and minerals to form rocky mounds. On Earth, we call these formations stromatolites, living records of our planet's earliest life, some dating back 3.5 billion years. But here's the twist: Mars' version might have been even stranger. Without Earth's tides or abundant oxygen, Ionia's reefs could have grown in ways that defy our expectations, their shapes and chemistries sculpted by a world with different rules. The evidence lies in the rocks. Orbital images of Ionia Terra reveal strange, concentric patterns in ancient sedimentary layers, ripples that look eerily similar to fossilized microbial reefs found in Western Australia's Shark Bay. But what's truly compelling are the minerals. Spectrometers have detected iron-rich hematite and silica deposits here, compounds often linked to microbial activity on Earth. Picture a Martian stromatolite, not the greenish domes we see in Earth's tidal flats, but rust-colored towers tinged with blue, their layers alternating between iron oxides and silica as the microbes responded to shifting water chemistry. These wouldn't have been static structures. Like Earth's reefs, they'd have pulsed with life, their growth speeding up during wet periods and stalling during droughts, leaving behind a geological fingerprint of Mars' climate swings. Yet Ionia's reefs faced challenges unimaginable on Earth. Mars' weaker gravity would have changed how sediments settled, possibly creating looser, more porous structures. The thin atmosphere offered little protection from UV radiation, forcing any reef-building microbes to thrive deeper underwater or develop protective pigments. And then there's the water itself, likely more acidic and saline than Earth's early oceans, laced with sulfates and perchlorates. Extremophiles in places like Chile's Laguna La Brava show us life can adapt to such extremes, building stromatolites in blood-red, hypersaline lagoons. But could Martian microbes have done the same? The answer might lie in the reef's microstructure. On Earth, fossilized stromatolites preserve microscopic textures, tiny bubbles where gas was trapped, or wrinkled patterns left by microbial mats. If Mars reefs left similar traces, future rovers could spot them with high-resolution microscopes, turning abstract speculation into undeniable proof. The real intrigue isn't just whether these reefs existed, it's what their demise reveals about habitability limits. stromatolites on Earth declined when oxygen levels rose and predators evolved. But on Mars, the end would have been environmental. As the planet dried, Aeonia's shallow seas would have evaporated, leaving the reefs exposed. The microbes might have fought back, adapting to life in shrinking brine pools or retreating underground. But eventually, even the hardiest survivors would have met their match. Their fossilized remains, if found, would be more than curiosities. They'd be time capsules, capturing the exact moment when a world's life support systems failed. Searching for these relics isn't just about Mars. It's a dry run for exploring ocean worlds like Europa or Enceladus, where icy shells might hide similar structures. Aeonia Terra's silent reefs challenge our assumptions about where life can take root and how creatively it can shape a world before the lights go out. Nili Patera's volcanic sands hide a mystery that could rewrite our understanding of Mars' flickers of methane gas seeping from cracks deep beneath the surface. These aren't just geological quirks. On Earth, methane seeps are bustling oases of life, where entire ecosystems thrive in the dark, fueled by chemical reactions rather than sunlight. Picture tube worms swaying in the Gulf of Mexico's depths, or bacteria in Arctic permafrost turning methane into energy. If Mars seeps follow the same script, they could be the closest thing to a welcome sign from an alien biosphere, past or even present. The chemistry is tantalizing. Methane shouldn't last long in Mars' atmosphere. Sunlight breaks it down within centuries. So when orbiters and telescopes detect periodic plumes, it means something is replenishing the supply. Volcanic activity could explain it, but Nili Patera's volcanoes have been silent for millions of years. That leaves two possibilities. Either the gas is being produced by subterranean minerals reacting with water or by something alive. On Earth, over 90% of methane emissions come from biological sources, from wetlands to cow stomachs. If Mars seeps share that pedigree, they might be the exhales of microbes buried deep in the planet's crust, surviving in pockets of brine or clinging to mineral-rich fractures. What makes these seeps so compelling isn't just the methane, it's the company it keeps. Nili Patera's seeps coincide with patches of serpentine, a mineral that forms when water interacts with olivine-rich rock. On Earth, serpentine vents often host methanogens microbes that produce methane as a byproduct of their metabolism. It's a cosmic coincidence too striking to ignore. Imagine a network of damp cracks beneath Nili Patera, where hypothetical Martian microbes munch on hydrogen and carbon dioxide, exhaling methane as waste. These organisms wouldn't need sunlight or surface water, just warmth from the planet's interior and a trickle of liquid seeping through the rocks. Yet the skeptics raise valid points. Methane can indeed form without life through processes like serpentinization, where water reacts with certain minerals. Mars' thin crust might be riddled with these reactions, especially in volcanic regions like Nili Patera. But here's the twist. Even abiotic methane seeps on Earth attract life. Bacteria cluster around them, turning the gas into energy. If Mars seeps were ever wetter or warmer, could they have done the same? The answer might lie in isotopes. Living organisms prefer lighter carbon atoms, leaving a distinct signature in the methane they produce. Future missions could analyze Nili Patera's gas plumes for these telltale fingerprints, a cosmic detective story written in atomic weights. The haunting question isn't just whether life exists there now, it's how long such a system could endure. Earth seep ecosystems rely on constant replenishment from active geology. Mars' interior is colder, its energy waning. Any organisms here would be living on borrowed time, their habitats shrinking as the planet's heart cools. But extremophiles have surprised us before. In South Africa's gold mines, bacteria survive in isolated pockets of water untouched by the surface for millions of years. If Martian microbes found a way to tap into the planet's dwindling heat or chemical gradients, they might still cling on, their existence marked by those faint methane whispers escaping into the sky. Nilipatera's seeps are more than a scientific puzzle, they are a test of life's universality. Whether the gas comes from chemistry or biology, it forces us to confront how little we know about the hidden corners of our solar system. As we stare at those spectral plumes from orbit, we're not just studying Mars, we're peering into the shadows, wondering if something, anything, is peering back. When NASA Phoenix lander scraped the dusty surface near Mars' North Pole in 2008, it uncovered something unexpected, streaks of perchlorate salts mixed into the soil. These weren't just any salts. Perchlorates are cosmic antifreeze, capable of turning frigid Martian ground into temporary oases by lowering water's freezing point by up to 70 degrees Celsius. Picture tiny veins of brine forming in the red dirt, liquid water surfacing in a world where it should be impossible. On Earth, from Chile's Atacama Desert to Antarctica's dry valleys, similar brines teem with life bacteria, algae, even tiny invertebrates that treat these toxic soups like home. If Martian perchlorate brines ever existed beyond fleeting droplets, they could have rewritten the rules of where life might cling on. The magic lies in how these brines behave. Unlike pure water, which would freeze or evaporate instantly on Mars, perchlorate solutions can stay liquid for weeks or even months in the right conditions. Phoenix's weather station recorded humidity spikes and temperatures just above -20, conditions where salty films could coat soil grains like microscopic dew. For extremophiles, that's all the real estate they'd need. On Earth, organisms like Planococcus halocryophilus thrive in Arctic permafrost brine veins, metabolizing at temperatures as low as -15. Mars brines might have offered a similar foothold, hypersaline microhabitats where microbes could eke out an existence between freezes. Yet Mars' version of this story comes with twists. Perchlorates aren't just antifreeze, they're powerful oxidizers that shred organic molecules on contact. For Earth life, they're poison. But extremophiles here have shown us that biology can turn even toxins into tools. Some bacteria in Nevada's perchlorate-laced springs use the salts as energy sources, breaking them down to release oxygen for respiration. If Martian microbes evolved similar tricks, their brines might have been biochemical furnaces hostile to us, but perfect for organisms built to exploit them. The challenge: these habitats would have been erratic. As Mars' climate swung between wet and dry phases, brines might have formed and vanished like mirages, forcing any inhabitants into cycles of dormancy and frantic activity. The real test lies in the chemistry Phoenix left unexplored. While the lander detected perchlorates, it couldn't search for organic molecules that might hint at past life. Future missions could drill into these salty soils, hunting for lipids or proteins adapted to perchlorate-rich environments. Even more compelling would be finding modern brines, something orbital radar has hinted at beneath Mars' south pole. If liquid perchlorate solutions still exist today, they could be the ultimate time capsules, preserving not just fossils, but potentially living cells in suspended animation. What makes these brines so fascinating isn't just their potential to host life, it's how they force us to rethink habitability. A microbe thriving in Martian perchlorate sludge wouldn't just be surviving, it would be playing by rules we've barely begun to decode. As we study Phoenix's long, cold landing site from orbit, those faint salt stains whisper a provocative question. If life can flourish in Earth's harshest brines, why not in the toxic, fleeting dampness of a world that refused to give up its water without a fight? Elysium Planitia stretches across Mars like a vast, frozen lava field, but beneath its cracked surface, orbital radar has detected whispers of a wetter past. Long after the planet's rivers dried up and its lakes turned to dust, this volcanic plain might have harbored something extraordinary, secret oases fed by underground springs. Picture pockets of liquid water seeping up through fractures in the rock, creating damp sanctuaries where life, if it existed, could have staged its last stand. These weren't the grand lakes of Mars' youth. They were desperate refuges clinging to existence in the planet's twilight years. The clues lie in Elysium's geology. Satellite images reveal networks of sinuous ridges, features that, on Earth, often trace the paths of ancient groundwater channels. Nearby, mineral stains hint at hydrothermal activity, where volcanic heat might have melted buried ice, sending warm water bubbling to the surface. But what's truly compelling are the landforms called rootless cones, mounds of sediment that look like they were blasted apart by steam explosions. On Earth, similar features form when groundwater meets subterranean magma, creating geyser-like eruptions. If Mars oases followed the same script, they wouldn't have been tranquil pools, but dynamic systems, steaming vents surrounded by mineral-rich ponds, their waters shifting with every tectonic sigh. For extremophiles, these oases could have been a lifeline. In Earth's deserts, from the Sahara to the Namib, isolated springs host entire ecosystems adapted to scarcity. Microbes like Crucoccytiopsis survive by sheltering under translucent rocks, photosynthesizing through quartz. Others, like Deinococcus radiodurans, withstand blistering UV radiation and extreme dehydration. If Martian organisms existed, Elysium's oases might have offered similar strategies: shaded crevices where water pooled, or mineral crusts that trapped humidity like tiny greenhouses. But Mars added brutal twists. With no ozone layer, surface UV would have been lethal. Any oasis dwellers would have needed to exploit the narrowest of damp margins, perhaps living beneath thin layers of sediment or inside porous rocks, where capillary action drew up moisture. The haunting question isn't just whether life persisted here, it's how long these oases could have lasted. On Earth, desert springs endure for millennia, fed by distant rainfall or deep aquifers. Mars' version would have been far more fragile, dependent on dwindling geothermal heat or the slow collapse of underground ice pockets. As the planet's core cooled, the springs would have faltered, their waters freezing or evaporating into the thin air. Any organisms relying on them would have faced a grim countdown: adapt, migrate, or perish. Yet even in their death throes, these oases could have left clues. Hydrothermal systems are notorious for fossilizing their inhabitants. In Iceland's H. Verivelia, silica-rich waters turn microbial mats into stone within years. Mars' equivalent might have preserved similar snapshots: layered deposits where biofilm textures are etched into mineral crusts, or microfossils trapped in vein-like mineral deposits. Future missions could target these relics, drilling into Elysium's dried springs to search for cellular shapes or chemical imbalances that defy abiotic explanations. What makes Elysium Planitia's lost oases so compelling isn't just their potential to have harbored life. It's their reminder of how stubbornly biology clings to even the slimmest opportunities. These weren't the planet's grandest ecosystems, but they might have been its last, tiny, tenacious eddies in the cosmic current, resisting the pull of extinction until the final drop was gone. As we study their fossilized remains, we're not just reconstructing Mars' past, we're measuring the universe's patience and how long life can stretch a moment into an eternity. Planitia's cracked, sun-baked plains might seem like just another barren wasteland, but hidden within its layered sediments could be one of Mars' most tantalizing secrets: fossilized mudflats that once teemed with life. Picture this: billions of years ago, after seasonal floods receded, vast stretches of sticky Martian mud dried under a pale pink sky, capturing imprints of whatever crawled, slithered, or grew across its surface. On Earth, from the dinosaur tracks of Texas Paluxy River to the billion-year-old microbial mats preserved in Australia's Dresser Formation, mudflats are nature's ultimate record keepers. Their fine-grained sediments trap footprints, ripples, and even the delicate textures of single-celled organisms with astonishing fidelity. If Mars ever hosted life, Chrysa's mudflats might have immortalized it in clay, waiting for us to decipher its story. What makes these potential mudflats so compelling is their chemistry. Chrysa's Planitia's low-lying basin was once a catchment for floodwaters from massive outflow channels like Erie's valleys. As those torrents slowed and spread across the plain, they deposited layers of silt and clay, the perfect materials for preserving biological signatures. On Earth, such environments fossilize more than just bones. They capture the fleeting moments of existence. In Namibia's Etosha Pan, for example, rain transforms cracked clay into temporary lakes, and when they dry, the mud records everything from bird tracks to insect trails. Mars' version could have done the same, its iron-rich clays hardening like concrete around the impressions of microbial mats, or just maybe, the faint footprints of something larger. The real intrigue lies in the details. Mud doesn't just fossilize shapes, it preserves behaviors. On Earth, fossilized ripple marks tell us about ancient currents, while cracked polygons reveal cycles of wet and dry. In Chrysa's mudflats, similar features could reveal how Martian life interacted with its environment. Did microbes form tangled mats that stabilized the sediment, leaving behind wrinkled textures like those in South Africa's 2-billion-year-old Barberton greenstone belt? Or did hypothetical multicellular organisms, even something as simple as a worm-like creature, drag its body through the mud, creating grooves that hardened into permanence? The difference between wishful thinking and science hinges on the subtlest of traces. A rover's high-resolution camera might spot the telltale dimples of gas bubbles trapped by decomposing organic matter, or the branching patterns of mineral veins formed by microbial metabolism. Yet Mars' mudflats pose challenges Earth's never faced. Without plate tectonics to bury and protect these layers, Chrysa's sediments have been exposed to radiation, dust storms, and temperature swings for eons. Any fossils here would be fragile, perhaps eroded to near invisibility, but there's hope. In Earth's driest deserts, like Chile's Atacama, mud cracks have preserved microbial remains for millions of years. Mars' weaker weathering might have done the same, its fossils hiding in plain sight, disguised as mundane mineral stains until viewed up close. The search for answers isn't just about biology, it's about time. Mudflats are snapshots, freezing moments that might have lasted only days. If Chrysa's layers captured life in action, they could reveal not just what existed, but how it lived. Did organisms cluster near evaporating puddles? Did they follow the retreating waterline like Earth's shoreline microbes? Every cracked polygon, every ripple mark could be a clue. Future missions might turn these speculations into certainty. A rover equipped with a drill could extract core samples from Chrysa's mudstones, analyzing them for microscopic textures or chemical imbalances that betray ancient life. Even more daring, a helicopter-like ingenuity, but with a microscope, could scout for outcroppings where wind has exposed pristine mudflat layers. Chrysa's Planitia's silent flats are more than geological relics. They're pages in a cosmic diary, waiting for us to learn their language. Whether they hold fossils or just the ghostly echoes of a habitable past, their message is the same. Even in a desert, the universe writes its secrets in mud. Beneath the layered ice of Mars' north polar cap, Planum Boreum, lies a mystery that defies the planet's frozen surface, potential lakes of liquid water buried under miles of ice. Unlike the fleeting puddles or ancient riverbeds we've explored elsewhere, these hidden reservoirs could still exist today, locked away in perpetual darkness. Picture this: vast, ice-sealed chambers where water remains liquid not because of the sun's warmth, but due to the crushing pressure of overlying ice and the faint geothermal whispers from Mars' core. On Earth, Antarctica's Lake Vida offers a stunning parallel, a body of water trapped under 60 feet of ice for thousands of years, yet teeming with microbial life that thrives in isolation. If Mars' polar cap holds similar lakes, they could be time capsules, preserving ecosystems that vanished from the surface eons ago. The evidence comes from orbital radar scans that reveal bright, reflective patches beneath Planum ice, signatures eerily similar to those of subglacial lakes on Earth. These anomalies suggest pockets of liquid water, likely kept from freezing by salts acting as antifreeze. But here's what's fascinating: Mars' polar lakes wouldn't be stagnant. On Earth, subglacial lakes like Vostok are dynamic systems, with currents driven by geothermal heat and the slow movement of ice. If Mars' buried lakes are equally active, they could circulate nutrients and minerals, creating habitable zones where life, if it ever existed, might still cling on. Imagine a Martian microbe, not unlike those in Antarctica's dark depths, metabolizing sulfur or iron in a world untouched by sunlight for millions of years. Yet the challenges are staggering. Without Earth's geothermal energy or tidal forces, Mars' subglacial lakes would be far more isolated, their chemistry shaped by slow, grinding processes. The water might be hypersaline, even toxic by our standards, with perchlorates or heavy metals dissolved in high concentrations. On Earth, organisms in places like Chile's Laguna Tebon, which thrive in similarly harsh brines, but Mars' lakes would push survival to the absolute limit. Radiation wouldn't be an issue, the ice shields against that, but energy would be scarce. Any life here would need to exploit the faintest chemical gradients, perhaps feeding on hydrogen released by reactions between water and rock, or clinging to mineral surfaces like microbial films in Earth's deepest caves. What makes these buried lakes so compelling isn't just their potential to harbor life, it's their defiance of time. While Mars' surface water evaporated or froze billions of years ago, Planum hidden lakes could have persisted, their ecosystems evolving in slow motion under the ice. If life ever took root here, it might have adapted to a world where change happens over millennia, not seasons. The fossils, if they exist, wouldn't be impressions in rock but living relics, organisms frozen in stasis, waiting for a drill to break the seal. The search for answers will require more than orbiters. Probing these lakes would mean melting through ice thicker than Earth's tallest mountains, all while preventing contamination from terrestrial microbes. But the payoff could redefine our place in the cosmos. Finding life in Planum darkness would prove that biology can flourish in the universe's most unexpected corners, not just where conditions are ideal, but where they're barely possible. And if the lakes prove sterile, that silence would be just as profound, a reminder that habitability alone doesn't guarantee life. Either way, these ice-buried lakes aren't just geological oddities. They're the universe's way of asking how far life can go, and how long it can wait before someone comes looking. Terra's cracked, mineral-stained plains hide one of Mars' most intriguing vanishing acts: shallow ponds that evaporated under the planet's thinning atmosphere, leaving behind chemical signatures like cosmic breadcrumbs. These weren't vast lakes or raging rivers. They were transient pools, some no larger than a backyard swimming pool, their waters shrinking under the relentless sun until only crusts of salt and clay remained. On Earth, from Death Valley's Badwater Basin to Bolivia's Salar de Uyuni, evaporating ponds are nature's concentrators trapping and preserving organic material as the water vanishes. If Mars' ponds followed the same rules, their dried sediments could be treasure chests, locking away molecular clues to life that might have clung to these fleeting oases. The magic lies in the chemistry. As water evaporates, it leaves behind whatever was dissolved in it: salts, minerals, and crucially, organic compounds. Margaritifera Terra's ponds, detected through orbital spectrometers, are rich in sulfates and chlorides, minerals that on Earth often form halos around fossilized microbial mats. Picture a Martian pond in its final days, a shrinking circle of brine, its edges crusted with white salts, its remaining waters turning syrupy with concentrated nutrients. For any organisms here, this would have been a race against time: adapt to the rising salinity or perish. On Earth, microbes in evaporating ponds employed desperate strategies. Some, like the salt-loving halobacteria, pump potassium into their cells to balance the external salt crush. Others secrete protective biofilms, creating tiny humid chambers in the drying mud. If Martian life existed, Margaritifera's ponds might have forced similar innovations, perhaps organisms that evolved to metabolize perchlorates, turning Mars' toxic salts into survival tools. Yet these ponds weren't just death traps, they were time capsules. On Earth, evaporite deposits in places like Australia's Shark Bay preserve microbial remains with staggering fidelity. Silica-rich waters can fossilize entire mats of cyanobacteria within weeks, their cellular structures intact for billions of years. Mars' weaker gravity and lack of plate tectonics might have made its evaporites even better at preservation. Without Earth's relentless geological recycling, Margaritifera's dried ponds could have sat undisturbed for eons, their delicate chemical clues shielded from destruction. The irony is poetic. The very process that killed these habitats' evaporation might have immortalized their inhabitants. The real mystery isn't just whether life existed here, it's how we'd recognize its traces. Earth's evaporating ponds leave behind layered archives, lipid molecules sandwiched between salt crystals, or isotopic ratios skewed by metabolic activity. But Mars' ponds have been baked by radiation and scoured by dust storms. Any biosignatures would be fragmented, their original patterns scrambled. Future missions could tackle this puzzle by targeting the pond's deepest layers, where minerals like gypsum might have sealed away organic material. A rover's drill might uncover microfossils resembling Earth stromatolites, or detect chemical echoes of proteins adapted to hypersalinity. Even more tantalizing, if some ponds evaporated rapidly, they could have trapped cells mid-cycle, snapshots of Martian biology frozen in its final moments. Margaritifera Terra's ghostly ponds are more than geological relics. They're experiments in extremes, testing life's ability to endure and leave a mark in a universe that seems hell-bent on erasing it. As we study their dried beds from orbit, we're not just searching for fossils. We're asking whether life, when cornered by a dying world, can still write its name in the salt. Vastitas Borealis sprawls across Mars' northern plains like a frozen wasteland today, but hidden in its cracked terrain lies evidence of a heartbreaking finale, the planet's last stand for habitability. This vast basin, once cradling shallow seas and sprawling wetlands, might have been the final refuge where liquid water, and any surviving life, made its desperate last stand before Mars crossed the threshold into permanent freeze. Picture this, a landscape of shrinking ponds and dwindling groundwater seeps, their waters growing saltier with each passing century as the planet's atmosphere leaked into space. While most of Mars had already turned to dust, Vastitas Borealis clung to moisture like a cosmic life raft. its damp soils and icy margins offering sanctuary just a little longer than anywhere else. What set this region apart wasn't just its water, it was its resilience. Nestled in the planet's northern lowlands, Vastitas Borealis benefited from lower elevation, where slightly higher atmospheric pressure might have allowed liquid water to persist even as other regions froze solid. Orbital data reveals ancient shorelines etched into the basin's edges, their contours suggesting a slow, agonizing retreat over millions of years. But here's the haunting detail. These shorelines aren't crisp like those of a stable sea. They're fragmented, discontinuous, hinting at a body of water that sputtered in and out of existence, its levels yo-yoing as Mars' climate unraveled. For any organisms still clinging on, survival would have meant adapting to cycles of abundance and scarcity, unlike anything we see on Earth. The real tragedy lies in what finally killed this last bastion. Unlike Earth, where oceans are replenished by rainfall and rivers, Vastitas Borealis water likely came from a dying source, subsurface aquifers draining their final reserves or melting permafrost that couldn't recharge. As the planet's core cooled, geothermal heat faded, shutting off the taps that fed these oases. The water didn't just vanish, it left behind chemical scars. Spectrometers have detected thick layers of magnesium and calcium sulfates minerals that form when brines evaporate completely. On Earth, such deposits in places like Chile's Salar de Atacama are graveyards for microbial communities that thrived until the last drop was gone. If Mars' final ecosystem followed the same script, its end wouldn't have been a dramatic collapse but a slow suffocation, life's final whispers etched in salt. Yet even in its death throes, Vastitas Borealis might have staged one last act of defiance. Some researchers speculate that transient pockets of brine could have lingered underground, shielded from the freezing surface by layers of insulating sediment. On Earth, life thrives in similarly hostile refuges, bacteria buried deep beneath Antarctica's ice, or fungi surviving in nuclear reactor coolant tanks. If Martian microbes existed, they might have retreated into these subterranean cracks, metabolizing at rates so slow they'd seem dormant to us. The question isn't just whether life died here, it's how long it took to surrender. Future missions could rewrite this elegy. A rover equipped to drill into Vastitas' sulfate-rich plains might uncover microfossils preserved like flies in amber, their cellular structures frozen in time. Even more compelling would be detecting organic molecules arranged in patterns that defy non-biological explanations, perhaps lipids clustered in membranes, or carbon isotopes skewed by ancient metabolism. Until then, this silent basin stands as a monument to impermanence, a reminder that even the hardiest ecosystems are at the mercy of a planet's fading heartbeat. The story of Vastitas Borealis isn't just about Mars, it's a preview of what could await any world when its star grows colder, its skies thinner, and its last water slips away. From vast oceans to hidden aquifers, Mars once hosted environments where life could have thrived. Each of its 37 vanished ecosystems, a chapter in a story of planetary transformation more dramatic than any fiction. Imagine standing on the edge of Jeziro crater 3 billion years ago, watching river water cascade into a lake teeming with potential, or descending into the damp caverns beneath Pavinus Mons, where geothermal warmth might have sustained subsurface life long after the surface froze. These weren't just random pockets of water, they were interconnected stages in Mars' slow-motion tragedy, each one a battleground where habitability fought against the inevitable. The real revelation isn't just that Mars was wet, it's how creatively water persisted. In Arabia, Terra, seasonal rivers carved valleys over millennia, while in Nili Fossi, groundwater seeps created micro-oases in the cracks of a dying world. Some ecosystems, like the subglacial lakes of Planum, might even cling to existence today, their secrets locked under miles of ice. This diversity mirrors Earth's extremes, from Antarctica's brine lakes to Yellowstone's acidic hot springs, proving that life, if it existed, had countless niches to exploit. Yet Mars' story diverges in one crucial way. Its biosphere, if it ever flourished, faced a slower, crueler end. Unlike Earth's mass extinctions, which reshaped life in sudden catastrophes, Mars' demise was a drawn-out whisper, atmospheres leaking away, waters evaporating or retreating underground, until even the hardiest survivors ran out of refuges. What makes these lost ecosystems so compelling isn't just their past, it's their future. Every dried delta, every salt-crusted playa is a time capsule waiting to be cracked open. NASA Perseverance rover is already caching samples from Jeziro's ancient lakebed, while ESA's ExoMars mission plans to drill 2 meters into Oxia Planum's clays. But the real breakthroughs may come from missions we've only dreamed of, robotic drills reaching Morth Valley's brackish estuaries, or submersibles exploring the hypothetical depths of Hela's Basin's buried lakes. Each expedition will test a fundamental hypothesis that life isn't a fluke, but a cosmic inevitability when conditions align. Yet even if Mars never hosted life, its ghosts hold lessons. The planet's decline is a cautionary tale about habitability fragility. Earth's magnetic field, Moon's stabilized axis, and relentless geological activity make it a paradise compared to Mars, but for how long? Studying these 37 ecosystems isn't just about unraveling the past. It's about anticipating futures that might await worlds like ours. The red planet's silence so far isn't a verdict, it's an invitation. Every unanswered question pushes us to dig deeper, to build better tools, to rethink what life could look like. Whether future missions find fossils, chemical echoes, or nothing at all, each discovery will reshape our place in the cosmos. So stay curious. The next chapter of this story might be written by a rover's drill, an orbiter's camera, or maybe even boots on the ground. Until then, Mars keeps its secrets, but every crater, canyon, and clay deposit brings us closer to the truth. If you're ready for the next revelation, hit subscribe. The universe has more mysteries to uncover, and we're